Hello and welcome. My name is Rafał Motriuk. I'm a science and technology journalist and I'll be your host today. Thank you for having me. Our event is called Code Dive. Welcome everyone. We're back for another annual Nokia Code Dive conference. It's our 8th, and I know so many of us enjoyed those previous years. You might enjoy this year's conference even more because it's the most technically advanced so far. We've learned so much after last year, which was our first exclusively online event. It's done again as live, so we make it appear as if it is in real time, but in fact, we've recorded the whole thing in advance. And we're broadcasting from Wrocław, a Nokia hub in Poland. Now, Code Dive is an annual event gathering IT professionals and programming enthusiasts to share new ideas, discuss current trends, and exchange experiences. We'd like to encourage knowledge sharing and provide a platform for networking. Since Code Dive speakers are active programmers themselves, they can present a practical approach, talk about actual experiences and real-life case studies. And we always follow hot topics and address the current demands of the IT world. Q&A sessions with the speakers will be held after each talk. So again, although we are pre-recording, the speakers will be live on Slack to answer your questions today. And now I'd like to give the cyberspace to Taras Lukaniuk, head of Nokia's Wrocław Technology Center. Taras, over to you.
Thanks, Rafał. Hello, everyone. I would like to welcome you all to the 8th edition of Code Dive conference. If I would be asked to describe this event within one word, I would definitely choose the word passion. It's a unique forum of passionates from all over the world. They're not talking about the topics. They are sharing with their passions with us. And today, we'll see a lot. IT, C++, 3D printing, algorithms, mathematics, and many more. And by the way, for today, we have prepared a small gift for you, or I should rather say, for your brain. The idea is coming from one person. So it's a great Nokian, the best subject matter experts I've ever met, and a friend of mine, Sławek Zborowski. His idea is called Hack Dive. You would need to have a small experience in cryptography and mathematics. We would like it to be a little bit challenging for you, but I'm pretty much sure you're gonna like it. You can accept the challenge soon after the conference, so stick around. With that said, I wish you all join in me and enjoy the day with Code Dive. The floor back to you, Rafał.
Thank you so much, Taras, for this introduction. And with that, I'd like to announce our first speaker of the day, Krzysztof Olszewski. Now, Krzysztof started his professional career in the IT industry in 2004 as a C++ developer at Siemens Mobile. Currently, he's a technical leader in the Nokia 5G continuous integration team. Over the years, he has worked with many different technologies, such as C++, Java, Python development, as well as being involved with mobile application development and full-stack development. He's also dealt with big data visualization and analyses, cloud solutions, DevOps, and continuous integration. As a typical physicist, his hobby is science, especially computer science, and in his free time he likes sailing and motorboating. He will be talking about Gerrit and Zuul in CI. Krzysztof, sail away.
Hello. Today I'll be talking about Gerrit and Zuul in continuous integration in large-scale continuous integration systems, because in a small scale we can use tools like Jenkins and it should be enough, but in the large-scale continuous integration systems we need to have something more, which will suit to us. So shortly about my presentation. This is only an overview of possible workflows. So it will cover only a rough overview of the features and the functionalities. I will not go into the deeply into the presented functionalities. It's just we don't have time for this. I will present some problems which we have during the software development process and possible solutions how we can solve those problems. I will focus on one particular workflow in our CI. This workflow should cover all possible scenarios. So it should be enough for almost every software development process. For in-depth knowledge, I will refer you to the tools documentation. The documentation is pretty good written, so it shouldn't be any problems to understand it. And also, there are lots of tutorials, so to set up such a system, you shouldn't spare a lot of time. It should be straightforward. And I will not talk about any other continuous integration systems like GitWeb or GitHub or whatever. I will just focus on this one, which I will present here. So what tools are used in the continuous integration? So there are many different setups with different tools. There are, of course, many different workflows, so we need to combine lots of tools. Sometimes one tool will be enough, but sometimes it's not enough, so we will have to provide some additional functionalities. The first tool which I'll be talking about is Jenkins. Jenkins is a job execution service, so it means that we can have a, let's say, building script, and those script needs to be triggered by something or provide results to some other systems. So with this, Jenkins comes with the help, so we can define such a job, so the steps which needs to be taken to process the source code, to release it, and so on. So for this, I'll be using Jenkins here. The next tool is a Gerrit. Gerrit is a source code control system, but with the capability of making the reviews on the code. So this is a code collaboration tool, I could say. We can learn from each other about the code. So this will also help the newcomers to learn from the most experienced developers in the teams. And the third tool is Zuul, together with a Gearman server. I will talk more later about this. But the main focus here is that the Zuul is a kind of bridge between the Gerrit, the source control system, and the Jenkins, the job execution system. So it will connect those two together. So a few words about the Jenkins. I will show you what creators of Jenkins are talking about the Jenkins, what it really is. So this is a continuous integration and continuous delivery system. It's pretty huge. We can implement simple CIs just with the Jenkins, and we do not need other tools. Of course, we need source control tools, but to have a small CI, Jenkins is typically enough. Installation of Jenkins is pretty easy, is straightforward. There are lots of tutorials, and usually it shouldn't take more than 1 hour to set up the Jenkins. Of course, we still need to set up the jobs, executors, and so on, but to just set up the Jenkins, it's a matter of minutes. Jenkins is very easy to configure. Everything we can do in the UI. Of course, we can also configure it with the XML files, for example, but anything what we would like to do, it can be done in the UI, and the UI is pretty well documented, and there is lots of help in every option. Jenkins is distributed. It means that it can schedule the jobs, the scripts which we are running on many other hosts. So in our case, it's more 1,000 of executors connected to the Jenkins. So Jenkins can use all of them, and only one instance of a Jenkins can handle lots of executors and lots of jobs. Jenkins is pretty extensible. So it's written in Java. It has its own language called Groovy, and we can extend this using the Groovy language. So we have access to the Jenkins internals, and it's pretty easy to extend its functionalities. And there are lots of plugins already written for the Jenkins. So if you are looking for something, most probably there is already a plugin for it available for the Jenkins, yes. What really Jenkins is? As I mentioned before, Jenkins is a job execution engine. So, for example, we would like to test the code and just simply run a build. And we would like to automate this. So what we can do is set up a simple job, which will build our source code, and then we will get the result if the code is compiling or not. And there can be lots of such types of jobs. For example, we can download, one job can download the sources, so it will connect to the SVN, Git, Gerrit, whatever. We'll download the source code, and we'll keep it as artifacts for the next jobs. We can do something like this, that one job can trigger another job. So, for example, here, first job will download the source code. Then we call the second job, which will prepare the environment for the build. Then the next job can be run, for example, the code checks like sanity, coverage, copy detection, or whatever. We can just check if the code is right and can be further processed. And if yes, then we actually can build the code, see if the code is compiling. And it's compiling, we can start another job. For example, we can do the test like a unit test, system component test, module tests, and so on. And after, when the test passed, for example, we can run our product on dedicated hardware. Yes, so we can send the build the whole product to the dedicated hardware and see how it behaves in the real environment. And finally, if everything works fine, we can release our product, update the documentation, for example, and probably we would like to deliver this product to our QA instances to be checked by the testers. So in general, Jenkins should be enough in most continuous integration systems. It does lots of job here, and it should be enough when we are talking about small scale CIs. So is the Jenkins a holy grail here for the CIs? Yeah, it's a pretty good solution. It can handle lots of jobs. It can handle thousands of executors, so it can be a really large system. Can be also configured to use cloud instances, for example. So in our case, we have an OpenStack cloud. So it can spawn the VMs there, run the jobs, and then kill those VMs. So it will act on request. And it also can be configured together with Kubernetes services. In a typical workflow, Jenkins is watching the source code repositories, and if it detects that there are some changes, it will run simple jobs on those changes. So if, for example, it will do the sanity check on the code, and if the sanity has passed, it will run a build, and so on. So something which I presented you before, this cascade can be implemented, but what to do when there is a faulty commit detected, yes? We have this commit already in our main line, and we see that there is a faulty commit. So what we can do here? So we need to at least make a fix for the commit or revert it. And Jenkins is not a good solution here, yes? So it's not a holy grail. And additionally, how we can organize the workflow with the code review. Jenkins is not also good at this point. But we have another tool which is called Gerrit, and here comes with the help. So some basic information about Gerrit. Gerrit is a code collaboration tool, so every commit which is coming to the Gerrit, we can comment on it. We can have a workflow with such a commit. So, for example, we will need some code guards to look into the code and say, okay, this code is good. We can proceed it further. It's of course it's open source, and in addition to the Git server, because Gerrit implements the whole Git stack, yes, under the hood there is a Git. So we are using standard Git client to communicate with the Gerrit, but with some additional options. And Git is missing the user management and the access right management, and this is present in the Gerrit. And the Gerrit has lots of plugins, so its functionality can be easily extended. Short history about the Gerrit. Everything started with the Mondrian project at Google. Developers at Google were saying that they have a pretty good tool to make a code reviews, but there was a problem with this tool. It cannot be public because it's used in Google-only services. So Google does not want to provide it to the public. But there was one guy who was working for Google, and he said, okay, maybe this project cannot go to public, but let's make something similar and make the developers happy. So he created the Rietveld project. But this project was using SVN. And as we know, SVN is a pretty old tool, so nowadays it's rarely used. Mostly Git is used. So although the Rietveld was missing some access control features, so they decided to make a fork from the Rietveld and to implement the access rules and switch it to the Git. And this was almost completely different product, so they decided to call it Gerrit. Gerrit Rietveld was a Dutch architect. And currently there are 3 versions. So the first one I've talked, it was a fork from the Rietveld. The version 2 changed implementation from Python to Java. So previously it was written in Python. In version 2 everything was rewritten to Java, and the SQL database was used. Currently we have a version 3, and the implementation of SQL has changed to NodeDB. There are some pros and cons about this. I will not talk about this right now. And also in version 3, the UI has changed. The previous UI wasn't so fancy, so they decided to implement the Polymer UI, which is called PolyGerrit right now, and it looks pretty good. And right now I will talk about Gerrit Essentials. So as I talk, Gerrit uses Git. It implements the Git stack. So all the Git commands are available also in Gerrit. And Gerrit has this additional functionality like emitting an events. Git doesn't have this functionality. And in Gerrit, for example, when there is a new commit approaching, Gerrit can send an event to the listening tools that, okay, we have a new commit approaching, and please react to this event. So those tools can react, okay, we have a new commit, so let's run some jobs, for example, or whatever. And Gerrit is also intended to teach and learn. So what does it mean? As a code collaboration tool, everyone is looking into the changes. So for example, if we have a team in which we have some newcomers and some more experienced developers, the newcomers can learn from those experienced developers just by doing the reviews. So they can ask why you implemented this in that way or whatever. And this helps to teach each other. And this prevents the errors occurring in the code. Okay, so there is one special thing about Gerrit. As it acts as the regular Git server, we need to tell Gerrit that we would like to use its functionality. So there is something called change ID. As you may know, in Git, every commit has his unique hash, yes, commit hash. And when you provide another commit, you will get another hash. So for the Gerrit to combine those commits, so we need to provide the change ID. So after the initial commit, we are generating such a change ID just to tell Gerrit that we would like to have this commit with the review. And any additional change to this commit, we'll have to have the same change ID so that the Gerrit knows, okay, here is the initial commit, and next commits are also connected to the first one, and those will be a patch sets for the initial commit. And to generate such a change ID, we need to use message hook functionality, which is provided by Git itself. So when we are typing git commit and so on, the script will be run by Git itself, and the script will look into the commit message if there is such a change or not. If there is no such a change ID, it will generate one for us. And here is an example how this works. So we are cloning the repository. We are downloading such a script from the Gerrit, and we are giving the execute rights to the script so that the Git can execute the script. Another thing which is only in Gerrit is a magic reference. So usually when you are pushing, you are telling that, okay, I'm pushing to this repository, to this branch. And this still works in Gerrit. But what if we would like to have a review process? So we need to use this magic reference, so this ref4. So for example, if we would like to push to the master, we are telling Gerrit, okay, we are pushing to this repository, to the head ref4 master. And for Gerrit, it means, okay, this commit must be merged to the master branch, but for now, I will create a review process for it. So there are still possibility that you can make a direct push to the Gerrit. It will mean that there will be no review created. So you will be directly pushing, and this will be automatically merged to the master, to the head of the branch by Gerrit. And in this case, we do not have a review. So when you will be looking into the Git history, you will see this commit, but there will be no review in the Gerrit itself. So this is really not advised, and this can make problems when we are using Zuul. I will talk about this later, how to solve it. Okay, so when we have such a review created, to be able to merge it to this commit to the head, some additional voting system must be satisfied. So for example, we are defining that each commit has to have a proper review process. So somebody has to look into the code and say, okay, this code looks good, can be processed further. I will show you how it works in our CI together with Zuul. And here we have some example view of the Gerrit UI. So on the top we have a menu where we can browse the repositories, browse the Git documentations, and so on. In the right upper corner, we have a search bar, so we can search the reviews. The filter is pretty large, so we can, in our case here, we are looking on the open changes, which are aged 1 week before. So we can see only those changes. And the first column is the subject of the change. The subject is taken as a first line from the commit message. So that if you have a long commit messages, so the first line will be the title, and the rest will be presented only in the UI here. The second column is the status. So right now I filtered it only to show the open changes. So there are no other changes. That there can be, for example, merge changes. Here we have a merge conflict. So here it means that there are two changes which are changing the same files, and there is a merge conflict between them, which should be solved by the developers. The next column is the owner. So who made this change? There can be more owners. For example, it can be an uploader or somebody who did the rebase and so on. But in this scenario, there is only the owner, so the one who pushed the change to the Gerrit. There is also a column called reviewers. Reviewers are the developers who are reviewing the change. I will talk a little bit more about this later. And of course, we have a repository to which this change belongs. We have a branch on which branch this change will be merged. And then we have a updated, so when the change was last updated. There is also a size of such a change. So Gerrit is able to determine how big the change is. If you are just changing, let's say, one line because we made a mistake and we are adding, let's say, some enum or whatever, and we are not changing much, then Gerrit will say, okay, it's an extra small change. But if you are doing some integration changes and we are changing hundreds of files, it will say that this is a pretty extra large change. So we can easily see the small, big changes and so on. The next columns are labels. I will talk about labels later, but of course we can filter those labels here. Okay, sorry, some interruption. Right now I will talk about the reviews which are made in Gerrit. And I already showed you how to create the review. So we need to push to this magic branch, and we need to have a change ID defined in our comments. And when we are pushing to the Gerrit, we can set some options already to the review. And some of the options can be, so for example, we can have a review in private state. So this will mean that nobody can see what we are doing with the code. It can be helpful with some security patches, for example, but please do not use it for security patches. There are different ways to do it. The private review is visible to us and some administrators who have a right to view the private reviews. And then when we say, okay, this was a private, but right now I can show to everyone. So the next option would be to remove the private. There is another state of the change, which is a work in progress. This is mostly used when we do not want to have a automatic CI system run for our change. Let's say we are working on some concept and we are sure that this code will not compile, but we would like to show this concept to other developers. So we are setting the review to WIP, and the automatic CI will not run for this review because it doesn't make sense. It will not compile, but we can share our approach to other developers. And when the review, they will say, okay, this looks good, please implement it. Then we can set it as ready, and the automatic CIs will be run on this code. We can also set hashtag for the review. It's just used to filter the reviews by the hashtag. We can put someone in the CC, so when we are pushing this for the review, the ones who are in the CC will be notified that there is a new review waiting, and maybe they are interested in the code. We can set reviewers. So, for example, we can set already teammates for this review. For the reviewers, there is a plugin which will automatically add the reviewers. So we are not providing the reviewers here during the push, because in our case, the reviewers are automatically added by the Gerrit itself. So, for example, we can define that everyone in my team will be a reviewer of my changes. And we can set the notify. So if somebody is watching source code, for example, one special file, changes to that file, he will be notified every time when somebody has changed this file, and we can just simply disable it. Next option which we can provide is a topic. Topic means that we would like to push few reviews at the same time. So, for example, we are doing some integrations. Yes, so one module needs to be in a higher version, and we need to integrate with other modules, with other products. And when we will provide only change in one module, it will break all other modules. So we need to provide, let's say, 5 changes in the same time. So when we will set the topic to those 5 changes, Gerrit will treat it as one change and will try to push all the changes together. If one of them fail, all of them will fail. So this is good functionality when we are working with many repositories and we need to push commit to all of them at the same time. The next option and the functionality is the labels. Labels are defined as stages, I could say. So, for example, we need to have firstly check the code. So we have a labels called verified. And the automatic CI can run a build, for example, in Jenkins, check if the code is compiling and so on, and then can put this code compiles, it looks good from automatic point of view, and we can start the review. So it will put the verified +1 on this review, and then actual review can happen. So the guys who are in the reviewers list can do the review, and then they are putting that, this change looks good for me, I will give the coach review +1. So we can define many such labels which needs to be fulfilled to be able to process this review further. And there are many other options. I will not talk about them. So, for example, the skip validation, so do not validate such a review. We can set a deadline, so after the deadline, the review will be automatically abandoned and so on. I refer you to the documentation. It's pretty good written, so all the options are there. Okay, so when we do the push to the Gerrit, it will give us a response message. If everything went fine, so the change is created, and it will provide us with the URL to such a change. And how does this look like? So here we have an example review. So I will start from the top. So we can see the status of the change. This one is, in the example, is in active state, so it's during the review process. Then we have a number which is generated by Gerrit, and it's just a review number. And then we have a title. And as you can see, and I told you before, this is the first line of the commit message. On the center, we have the commit message, which was provided by the developer. And on the bottom of the commit message, you can see this change ID, which I was talking previously. So every commit message has to have this change ID. And for Gerrit will group the commits by this change ID, which will be as a one review. On the right, we have some additional information. So, for example, if there are and others review which are connected to our. For example, we are a parent or another review, so this will be shown here. Also, we have a topic here, so the reviews which have the same topic will be merged together, and we have a list of such reviews. And when you are logged in, you will see additional menu. So you can do the rebase here. So we would like to change our parent to have the latest from the head. So we can do the rebase. We can abandon such a change. We can edit such a change. This is really helpful, this feature, because, for example, when you are on vacations and you get the call, oh, we need to implement something, or please look at this. This is critical for us, and you can edit the change here directly in the UI, so you don't have to have a working Git in your laptop or whatever. You can do this even on your mobile, so you can edit such a change pretty easily. And of course, we can cherry pick such a change, download it as a patch. We can even delete it. We can make a follow-up. So we implemented some feature, but something is still missing. We can do the follow-up, so those changes will be connected. We can set it as a work in progress, as I explained before. So we know that the code will not really compile, will not really work, and we do not want to waste the CI resources. So we are making it as a work in progress. We can also mark it as a private, as I was mentioning before, as a reviewed. If we are a reviewer for such a changes, when we are logging to the Gerrit, we see the dashboard. So there will be our changes, changes in which we are the reviewers. And when we click here as a mark as a reviewed, this change will not appear in our dashboard. And of course, we can also move this change between the branches. So for example, we are working on the master, but some branches also needs to be updated with such a change. So we can easily move this change to other branches. And right now, let's go back to the left side. So we can see the update time. So when the review was last updated, we have an owner here. So who uploaded the commit, the change here. We have a reviewer. So who is reviewing the code. Right now here in this example, we can see only Zuul. I will talk later about this. And we have SEC, so who was notified about this change. Of course, also we have here project and the branch to which change belongs. And we have a parent ID. So this change, let's say we made the change 1 week ago, and since that time there was lots of development ongoing, and the head is completely different than our parent, so we can click the rebase button, and our change will be rebased automatically to the current head of the branch. Next, we have this topic, which I was already talking about. And here we also have a strategy. So what Gerrit can do with such a change. So there are few possibilities. So this is one of them is fast forward only. So it will only do the merge when the fast forward is possible. So merge if necessary, always merge, cherry pick, rebase if necessary, and rebase always. Usually we are using merge if necessary and rebase if necessary. But it depends on the workflow and how to treat the commits there. Next, we have 3 labels here. You can see, so one of them is the code review, the second is verified, and the third is workflow. So this is just an example of the labels. I will talk more about this later and show you a bit different setup. Then we have labels which do not need to be satisfied. So we can put some additional labels, so we can have some additional workflow for it. And also we have a link to the Git web, so we can browse the repository, see the blames and whatever. And on the bottom of the review, we have actually the change itself. So what the change is changing, what files is changing, what is the commit message. We can see everything here. On the right side, you have those bars, so the green, the red one. The green is means that the code was added. The red means that the code was removed. And we have also div here, so we can see what are the difference between the base and the latest patch set. So I was talking about the patch set, but maybe some examples. So when we are pushing for the first time, there is a patch set 1 created. And we are working on the review, and let's say we are pushing some more fixes. So what we are doing in Git, we are doing the commit amend. So the commit message is not changing, the change ID stays the same, but we are pushing different files, let's say. So we can compare this between those patch sets, what was changing between the commits there, or we can compare it with the base, so with the initial commit. Below we have a log. So what was going on with this review? So every step is here. So on the right we have a patch set. On which patch set this was happening, and we can see that somebody was giving the verified, yes, the code review and so on. And usually, when looking at this, we can say how the workflow looks like and what was going with the change. Okay, so is the Gerrit and Jenkins a holy grail for the CI? So it looks pretty good right now, yes. So in most CIs, it should be enough, yes. So we have a code review process and we have some automatic jobs. So there is a plugin for Jenkins which talks with Gerrit. It responds for the stream events, and this should be enough in the small scale CI. But what if we must process hundreds of commits daily? Let's imagine that we have 10 commits daily, and one commit is triggering jobs on the Jenkins. So we need to check the sanity code, we run some tests, make a build, and this is taking time. Let's say altogether is 1 hour. And if we have 10 commits coming to our CI, so the first commit will be checked, will be rebased on the top, will be merged. Then the second one, and so on. So it will require 10 hours for the 11th commit to be able to merge to the mainline. So this is something, yeah, with 10 commits, 10 hours, okay. But what if we have 100 commits, yes? And we have only 24 hours for this. So this setup is not enough. And how to define the merge strategy. So what to do when there is a faulty commit detected, yes? So we need to revert it, we need to provide a fix. So not everything here is okay. And how we can speed up the delivery. So we have 100 commits waiting, so we will be waiting 100 hours to check all the commits and provide this to the customer. So not really. There is still something missing here. So there is another tool, which is called Zuul. Some basic informations. Maybe you already watched the Ghostbusters movie from the 80s. There was one monster who was called Zuul, the gatekeeper. So he was guarding the gate, and only some, in our case, some specific commits can enter the gate and can be processed. Zuul is also an open source project, mainly it is used together with Ansible. So the main implementation uses Ansible as a job execution service. Here we are using the German plugin together with Jenkins. So in our case, the jobs are executed by Jenkins. Zuul is subscribing to the Gerrit event. So anything which is ongoing in Gerrit, Zuul is receiving those information and can react on this. So for example, if there is a new review created, Zuul gets the notification there is a new review created. It's called patch set created. And Zuul, okay, here I have to run some verifying tests. So it talks to Jenkins through the German plugin and says, okay, please run some scripts, some jobs, and check if the code is okay. And when the Jenkins says, okay, it looks good, Zuul is giving verified +1, so it also votes on the Gerrit reviews. And what is a Zuul concept? The main concept is that it has to keep the history green. So Zuul is not allowing faulty commits to enter the mainline. So we can be sure that when we are going back in history and randomly taking some commits there, we can be sure that this commit will work. So for sure it will pass all the tests, can be released, and so on. And this is the main concept here, yes, to keep the history always green. Zuul does not save the resources. Zuul saves time. I will talk about this mechanism a bit later, but we do not want to wait, let's say, 100 hours to have 100 commits in the main line. Zuul will just need the resources and will speed this process pretty well. And the workflow, how the workflow is organized in Zuul. It's organized into the pipelines. Pipeline is a set of jobs which have to be executed and to pass the pipeline. In the main concept, there are 3 pipelines. The first pipeline is the check pipeline. So the check pipeline is executed when new commit arrives. Yes. So when there is a new patch set created. Yes. So let's say we are pushing for the commit for the first time, or we are updating already existing review with some changes, then Zuul listens to the events from Gerrit and says, okay, this commit needs to be checked in the check pipeline. So it runs all the jobs which are defined in the Zuul internal configuration. And usually those jobs are the subset of the gate jobs. Because another story is that Zuul, maybe I will talk about this later with the next pipeline, with the gate pipeline. So the gate pipeline is the pipeline which is executed after the review. Because the check pipeline is executed first, there is a review process not started yet, because we are not sure if the code is working, if it's even compiling, and so on. So we do not want to lose time of the reviewers to review the code which is not compiling, not working. So when the check pipeline is successful, then the real review process starts. The reviewers are looking into the code, and they saying, okay, this from our point of view, this code looks okay, it can be processed further. So the gate pipeline starts. Gate pipeline is a check before the merge. So it ensures that there are no failing tests. The code is compiling, the code can be merged and released, and so on. So the gate pipeline starts, and after the gate pipeline succeeded, such a change can be merged by Gerrit, and the change can be visible to Git. Because when you are pulling from the Git, you are cloning from the Git, and the changes which are in the active status, so during the review, they are not present in the Git. So in the Git, there are only changes which actually were merged by this gate pipeline. And there is a third pipeline, which is rarely used, but is a post pipeline. So after the Git Gerrit merges the change to the Git, the post pipeline is executed, and we can, for example, update the documentation during this. We can inform some other tools that we have a new release available, and so on. And also in the post pipeline, we can send our product to the QR environment so that the testers, QAs can test our release. Of course, this workflow can be easily extended. We can add additional pipelines. So in our case, we decided to add a pre-check pipeline because we do not want to run all the check pipelines all the time when the new patch set is coming. So for example, developer is looking into one specific feature and he does not want to run, for example, SCTs. So he just interested in the, let's say, code sanity, for example. So he can choose which jobs needs to be run. And after the pre-check pipeline, we can run the regular check pipeline. And few words about the Zuul component. So Zuul is organized by few components. One of them is the scheduler. Scheduler is the communication with the Gerrit. So it is receiving the Gerrit stream events. He can also make comments to the reviews. He can make votes in the Gerrit and so on. The next component is a merger. Merger is doing, as its name says, it's doing the merges. I will talk about those merges a bit later because it's a very important functionality of Zuul. So I will talk a bit later. There is a web server, so we can see the dashboard of the Zuul, what currently Zuul is doing, what jobs are running, and so on. We can see also the logs, and we can call any REST APIs which are implemented for the Zuul. And there is also a Gearman server. Gearman server is used to communicate between the Zuul components. And in our case, we are using the Gearman to communicate with the Jenkins. So let's assume that scheduler receives event that there is a new patch set created. Scheduler looks into its internal configuration, what pipeline should be executed, what jobs should be executed, and see this, and it's throwing to the Gearman. Okay, please run these jobs on this change, and I will wait for the results. What Gearman is doing is looking into its internal database and looks, okay, these jobs can be run by this server, by this Jenkins server, on this host, and is sending the information to the Jenkins. Please run this job on this host. Jenkins is running this job and is returning the status code to the Gearman. Gearman then informs the scheduler what to do, for example, to make a negative vote on the review because the build failed. This was just an example. And right now, the most interesting feature of the Zuul. Usually, CI systems are merging developers' changes to the mainline. If the regression is found, we need to do something with the commit which provide the regressions here. Yes. So as I said, we can revert this commit, or we can provide a fix for it. But in Zuul gating, it's a bit different. So Zuul needs to ensure that the merge secret is not breaking the code. So it prevents changes which are failing to enter to the mainline. So in the world of SVN, there was a thing that we need to keep trunk always green. In our case, we need to keep head always green. As I said before, we would like to have a functionality that in any time we would like to go back in the history of Git, and Zuul is giving us at least the hope that everything will work there. It's not perfect solution, but in our case, almost all commits which are present in our repository, you can go back in the history, run the test, and make sure that this is working. But as I said before, with a big number of developers and a big number of changes coming to our system, and big number of jobs which needs to be run by the Jenkins, this is very time consuming. And we need to have some merging approach to this. Because waiting 100 hours, it will not work in our case when we need to provide our product every day to the customer. Remember that we have a check pipeline. So check pipeline is ensuring that the code is working, is not breaking anything, and the review process can start. And check pipeline helps us with the gate pipeline, because if the change was working in the check, we can be almost sure with very high probability that it will also work in the gate pipeline. Yes. So if the change passed the check pipeline, almost in all cases, it will also pass the gate pipeline. The only difference is the parent, because when the change is entering the gate, it must be rebased to the latest head. So let's say that there will be 50 commits between the original parent and the parent after rebase. So most probably not too much has changed, because the project is pretty large and developers are doing commits in different modules and so on. So if the change already passed checked, we can be almost sure that it will pass also the gate. And how this is working? So let's assume that we have a repository with 2 changes already in it, and there are 3 developers which are pushing almost in the same time their work to the Gerrit. So they have the same parent, because they cloned in the same time when there is only the second commit available in the Git. So the parent, all of those 3 changes, parent is 2. And when the check pipeline is started, it started that the third change has a parent on the second change, and so on. So there will be 3 pipelines, concurrent pipelines running in the same time. But all of the 3 changes, the parent is the same. But when the change is entering the gate pipeline, we need to do some speculative merge. So Zuul is assuming, okay, the third change was working together with the second change. So in gate, it also should work. But the fourth change, previously it was working with the parent as a second change, and right now we are assuming that, okay, most probably the third change will be merged to the main line, so maybe the fourth change will also be merged together with the third. And the same is happening with the fifth change. And here is how it works. So let's assume that those first 2 blocks on the left, this is already present in the Git repository. Then 3 additional commits are pushed. So the C, D, and E. And what is doing Zuul? It's putting the C on the top of B, D on the top of C, and E on the top of D. And it's running in parallel jobs for those 3 changes. So we have 3 gate pipelines run in this case, and instead of waiting, let's say 3 hours, we will have a exact what was changed, what was checked here after 1 hour. But what if the change C is failing here? Yes. So, for example, it was possible to merge it in the check pipeline, but something has changed, and right now the C change cannot be merged into the main line. The D change. So the C was okay, but the D was wrong. So C is on the right now it's merged on the top of the B, so it's already present in the Git. But the D change is thrown away by the Zuul, so it is not compiling. It cannot be merged. And it's Zuul is doing the speculative merge again. So it's putting the E on the top of the C, and there is already commit F approaching, so it's put on the E. And everything starts again, so those pipelines will be started again with this setup, but this time without the broken commit D. Okay, so how does looks like the final workflow? Yes, we have a Gerrit with a Git repository inside, and we have a developer. Developer clones the repository here. He is doing some feature implementation, so he works, and after his work is done, he pushes the commit back to the Gerrit. Now Gerrit creates a new change, because this is the first commit with such a change ID. So Gerrit creates a new change. Then it emits a stream event to Zuul that there is a new patch set created. Zuul is looking into its configuration file, so what pipeline should be run, what jobs should be run, and Zuul is triggering the check pipeline. So through the Gilman, it is sending information to Jenkins, please run the check jobs. On the Jenkins, we have a configuration, so what the jobs are doing, what executors do we have. So Jenkins is running those jobs, and it sends back the results to the Zuul. Zuul is looking again into its configuration, and if all the jobs are green, so all the jobs passes, it's putting the label verified OK on the change in Gerrit. And right now the actual review process begins. So reviewer is looking into the change, into the code, and if everything is okay, he is giving the vote to the code review label +1 or +2. +2 in our case means that the review process is fully satisfied, when +1 means this looks okay, but somebody with a bigger experience should give +2. And such a review is getting +2, so it means that we can start the gate pipeline. So again, Zuul is notified about this, so Zuul is checks that there is a new label assigned to the change. So right now it is running the gate pipeline. So what it does, it's doing the rebase, because the change could be created a few days ago with a different parent, which was at that time. And right now, before the merge, he needs to be sure that the change can be merged to the repository. So Zuul is doing an automatic rebase of such a change, and it's doing also the speculative merge with other changes which could be waiting in the queue. And of course, it is running the Jenkins jobs. All the jobs are back with the results to the Zuul. So Zuul is, if everything was okay, Zuul is giving the gatekeeper +1, and this change is internally merged by Gerrit. And since that time, this change is visible in the Git. So if you clone the Git repository, this change will be there. And there is this third pipeline running, which is a post pipeline. And in this pipeline, we can do, for example, this documentation update. We can notify other tools that we have a new code base. We have an update, and so on. So are those tools combined together a holy grail for the CIs? So not really, not really. The setup is not error prone. So if there is one element missing, let's say that, for example, we cannot connect to the cloud executors, this will not work at all, yes? So our CI will be stopped. There is also a huge resource usage. So if we have, let's say, 20, 30,000 of cores, all of them can be used in just a matter of minutes. It only depends on how much resources do we have. And there are many other problems. For example, that frequent gate reschedule. So if the change is already in the gate, it's processing by the Zuul, and somebody says, okay, but I will have to upload something. So this change is thrown away from the gate, and the whole gate is rescheduled. And there are many, many different problems like this. So do we have a holy grail in CI? No, not really. We still have to look for it. Thank you for watching. That was all from my side.
Thank you so much for your insight and in-depth analysis. This was Krzysztof Olszewski, and this is Code Dive 2021. Stick around for more. We'll be back after this break. Now, many of you may remember our full-time speaker, Bartosz Szurgot. He's been with Code Dive since the beginning, and again, he's back by popular demand. We actually considered talking him out of speaking again, but then we remembered what a fantastic presenter he is, and here we are, Bartosz is with us again. His professional labels are C++, Linux and DevOps. Also, he's an expert in electronics, 3D printing, cybersecurity, algorithms, computer networks, vision systems, and artificial intelligence. He has been a speaker at many conferences and geek gatherings, including NDC Oslo, EMBO++, Wrocław's first C++ user group, and TEDx. After Hour, Bash contributes to the open source world on a daily basis. He has also co-authored multiple articles in Programista and Software Developer Journal magazines. So, 3D printing programmer's perspective. Bash, go ahead.
Okay. So, hello everyone, and welcome to 3D printing as seen from the programmer's perspective. As said, my name is Bartosz Szurgot, but I'm typically referred to as Bash because this happens to be a concatenation of first letters of my name and surname together, and also for a second reason because I'm a total nerd who loves Linux, and I'm also a C++ developer. Interested in DevOps movement. So aside from all of the interest that Adam presented, actually there is one more interesting on the list, which is 3D printing, and this will actually be a theme of today's talk. So at office hours, I work at QIAGEN, where I hold the position of a principal software engineer. So I can proudly now say that I work in the highest building in the entire city, even though the office is just on the first floor, but hell, you can't have everything, as they say, right? The name QIAGEN might not really ring a bell, but if you ever gave a blood sample for analysis, there is a really good chance that it has been processed with QIAGEN devices, chemistry, or both. So the name is well recognized in the medical industry. And the medical industry is actually something very interesting because it's probably the only industry in the entire world in which, where you get a positive result, it actually can mean a bad news for you. So working out there, here in Wrocław office, we are mostly working on software for devices for medical purposes and scientific purposes, including but not limited to those who help fight current ongoing COVID-19 pandemic. After hours, well, I'm a parent now, so most of the time I just try to get some sleep, like any sleep whatsoever. But still, I wouldn't be myself if I wouldn't try to nerd out at night anyway. And nowadays, it happens a lot around 3D printing. And this is, and the 3D printing is actually something that I would like to talk to you about today, but not just the 3D printing as seen through the eyes of the software engineer. Now, I promised this will be an introductory talk, so let me start with a little bit of introduction about 3D printing itself. So first, let's start with the high-level overview of the whole process. So first, you design a model on the computer, just like regular 3D mesh. Then you put it onto the printer, which creates it usually out of the plastic, and then you end up with a physical object in your hand. That's like a top-level overview. There are, of course, different ways this creation can actually happen. The common one is fused deposition modeling, or FDM in short, which works by heating up a fiber of plastic and extruding it through the very fine nozzle and putting it layer by layer by layer next to one another in order to create something in 3D. So conceptually, this is very similar to how regular 2D printers work, aside from the fact that we are now adding the third layer, the third dimension. So that's conceptually it, but that's not the only one. You can also have so-called SLS, or selective laser sintering, which works by using high-power lasers concentrated in a small dot to heat up the powder, sometimes a metal, and make it a solid in this place. So these are things which usually are found in industry setups because they can actually print in metal. And last but not least, there is an SLA, stereolithography, which basically prints in resin. There are different technologies available, but the core idea is to have resin which cures by shining UV light on it. And thanks to this, we can pull out of a bath of resin a 3D printed object. So it's like a third major option that you could use. So let's have a look at comparisons of all these three technologies. So in case of the FDM, the really nice thing is it's cheap and it has great community support with a RepRap project. It's also multi-material, so we can basically select from loads of different plastics to print with add-on of different colors. So there is an enormous amount of material to choose from. The process itself is also very clean. There are almost no leftovers from the print, so no material gets waste. And the devices themselves are really compact. There are, of course, downsides. So first of all, the process is very slow. And the second is very complex. So as long as things go right, it's all cool. But when the problems start to happen, you usually need to have a decent amount of experience and knowledge in order to diagnose any non-trivial issues. The second thing is SLS, so this high power laser part. So this one is very precise, and the key benefit here is that you can actually print in metal. So this is something that is, for instance, used in the space industry. The resulting parts are really strong compared to plastic ones, for instance, but the devices themselves are really large, are ridiculously expensive. Think of something like a price of a big flat. And the process is also very slow, and most importantly, it's also hazardous. So the powder that is being used to print is actually very, very fine. So if you happen to inhale it by accident, this can be a serious threat for your health. So because of that, you need to have a proper equipment, protective equipment for users of the printer. So this is not something that you will find at homes typically. And the last is the SLA, the resin printer, sometimes called a goo printer. The device is, again, fairly cheap. It's super fast. It's definitely the fastest out of all three. It's like faster by at least a row of magnitude and often even more. It produces very precise parts with a very fine layers. But in reality, in order to print in that, you usually need between 2 and 3 devices, which means additional costs and space. And the chemistry involved is toxic. It's not like deadly toxic, but it's toxic enough that you could get some serious allergies out of it if you are not sitting in a well-ventilated room, if the device is not in a well-ventilated room and you are actually in the different room while the printing happens. So it's not really convenient. It's doable at home, but not convenient. And the process itself is very dirty because the goo, the resin, usually ends spilling up all over the place, and it's very smelly. So usually you cannot sit within the same room with the printer. So for these reasons, from now on, when we'll be talking about 3D printing, we'll be just focusing on FDM 3D printing. So there are different options, but I think that FDM is most suited for home usage and for beginners. So we'll solely focus on that from that point on. So how our pipeline actually looks like. First, we need to have a CAD model. So we need to actually design the whole thing that we want to print. And in terms of comparison to programming language, let's say Java, this would be something like a Java code, the source code that you actually then compile. You compile it to the STL. STL is actually something like a lingua franca of all 3D printers, where you could, of 3D printing world actually, and you can think of it as a Java intermediate representation. So this is like a jar file that you deliver to the user so that they can run it on a computer. So in our case, the computer is the printer, and the machine code, which is executed there, is a G-code. G-code is something that originates in CNC machines. And it basically is a really huge list of movements of the head. So move to position XYZ, extrude a little bit, move to other position, extrude a little bit, and so on. So that's roughly how it looks like. So if you have an idea, you would like to create something and print it out in 3D, there are different tools for different jobs. Very common choice is Blender. This is an free and open source tool which can be used for modeling. This typically is used for modeling some artistic things, so something that doesn't really need to have very fine, precise dimensioning, but is supposed to look nice because it's like a sculpturing-like tool. If you are doing professional engineering, there is an Autodesk Fusion 360, which is a graphical tool which is designed to make parts, like mechanically working parts, with tight dimensions and do it very fast. The problem is that this is a closed source solution and it's actually commercial, so you need to pay for using this tool on an annual basis, I believe, and this is not exactly a cheap one. So unless you are doing a lot of 3D printing or doing it commercially, this probably will not be a viable solution for you. And last but not least, there is an OpenSCAD, which is a free and open source tool as well. But then you define a final shape that you would like to create in terms of a source code. So this is something really close to our world, the programming world. We have a source code here. So let's try to do a little bit of modeling in OpenSCAD. So what is OpenSCAD? Actually, this is one of these rare cases where when you see a logo of the system, it actually tells you a lot about it. So if you look at it, this is a sphere with cylindrical parts removed out of it. So there are 3 cylinders which are subtracted from it. And this is actually the core idea behind OpenSCAD. You are basically summing up or removing parts of the 3D objects. So this is how the IDE of the OpenSCAD looks like. There is a preview where you can see how how the component that you are designing will actually look like. Then on the left-hand side, you have a source code in which you actually apply commands that shall be executed to end up with this model. And of course, you have a warning/debug window where you can actually see what's wrong with the compilation or what the device's compiler would give you during the process. So you may notice that we used a source code and some 3D objects in one sentences. So what it means is linear algebra. But please don't panic. It's not really complex. Actually, in real life, you will barely ever use anything more than just adding some vectors in 3D or maybe multiplying a vector by a constant. And that's roughly it. So maybe as a first task, let's try to create something simple, like a hollow box which you could put something inside. So first, we start with a box like a regular cube. And this happens to be just a single module used inside OpenSCAD, which is called cube. And then we provide 3 dimensions, OX, OY, and OZ, as a single vector. So it takes a single parameter of a 3D vector and outputs a cube which is of appropriate size. You can also create some constant values, either string or a number or a vector of vectors, whatever you like. And also there are comments which you could put inside the code to make it more readable. So let's try to define some useful constant. So for instance, if we'll be using a size of our box many times, we can create it as a constant and then pass it to the cube. So the cube takes a size, and size is defined as a vector of 3 elements. So we get exactly the same result as previously, but now we have size defined on site. Now let's try to do object difference. So let's try to do this cut-in into our cube to have an actual box, not a brick. So there is a difference module which does exactly that. In its body, it takes a number of elements. The first element is a starting point, and then all the others are being subtracted from the original model. So these are like these cut-ins into the initial part. Here we only have a cube, so there's only one element, and there's nothing to subtract. So again, we end up with exactly the same model. But now, if we add something, we define a wall to be 1.5 millimeters thick, and we define another cube, which will be of the same size as previous one, minus 2 times wall and the vector 110. So this will actually create a vector of a size decreased by a wall and a wall in both OX and OY directions. So this will actually be our internal part. We do not need to decrease OZ because this is only the part of the offset of the box. Because you can see that actually something went really wrong here, right? We created 2 cubes of appropriate size, but instead of a box, we ended up with something like an extruded letter L. So it didn't work. We need to debug it. And there is actually an interesting thing for debugging in OpenSCAD, and it's called hash symbol. So we can put it in front of any object in OpenSCAD, and it will highlight it for you, even though the original object might not be visible by itself, because, for instance, it was something that was being subtracted from the original form. Here, we also shifted up by 1 millimeter up so that we can clearly see where the part is. And now we can also see where is the problem. So both our boxes originate at point 0, 0, 0, so the center of our axis. So what it means that even though we decrease the size by 2 walls, we decrease it from one end, not from the both as we intended. So this part is incorrect, so let's try to fix it. And to fix it, we use a translate module, which will shift our object by the wall size on OX, OY, and OZ. So now we have this wall thickness all around. And this translation applies only to the objects underneath it until the ending semicolon. So this block shifts the cube, resize it, and put it into the difference, so the element is removed from the overall object. So with removing of our debug let's call it a statement, we actually end up with the box we were looking for, which is great. But you might say, okay, aren't we doing a little bit too much thinking inside of the box, actually? Well, yeah, in a sense, yes. But actually, if you try to design an enclosure, thinking inside of the box is actually the way to go. So let's try to do it. But let's try to do something a little bit more fancy. Let's try to do a rounded box, so the box with a rounded edges, so that it's not sharp. You will not cut your fingers with it because the edge can be really sharp on the edges here. So let's try to do something about it. So first, we need to learn how to use a cylinder. And it's actually fairly straightforward. Again, for convenience, we'll create a couple of constant values, so we know size, and the corner radius. So this will be effectively the radius of the cylinder we are working on, and this will also be the radius of the corner on of our box. And now the cylinder. Cylinder basically takes two parameters, the radius and the height of the cylinder. And this is size of 2. So it actually takes the last argument of the size, which is a value of 20. So now our cylinder is fully parameterized, both with the corner radius and with the height of the box. Now, let's try to create multiple cylinders. And for this, as programmers, we would obviously use a loop. But first, we need to compute what will be the distance between the centers of the cylinders. So again, we take our initial size, and now we need to decrease it by this corner radius on both ends, right? On both OX and OY axis. And now the int s internal size will be the kind of like a box in between all of our cylinders. So having this size compute, let's try to dive into for loops. So dx goes from 0 to 1 with step of 1. So effectively, this will be a vector of two values, 0 and 1. The same goes for dy. And now we are actually computing translation. So it's not a fixed value. It's something that changes with each iteration of the loop. So for OX parameter, we go dx times our internal size of 0. So we take our distance and multiply by the dx, so either 0 or 1. So we effectively are in position or being moved. The same for dy. So we actually get 4 points, which effectively turns out to be the corners of our internal box. And in these corners, we put a cylinder of a specific radius and a specific height. And that's basically it. We have cylinders all over the place. But what we actually wanted to have is a box, right? So in order to do so, we need to create a hole around it. And it turns out there is a ready-to-go module which does exactly that. So for a given set of objects, you can create a shape which is something like a stretch tape all around all the objects that you have defined. So in our case, it's about these 4 cylinders, and the hull will fill up the space in between. So we end up with exactly what we were looking for. We now have the basic shape of the box with rounded corners. But you may notice that we actually will need some code duplications here. Have a look at the original code and the cube usage. So now the cube usage uses a size, but the module cube is already defined in OpenSCAD. So even though the two sizes are different and we need to compute them, the model itself is basically like a copy and paste name. But now we have a model of a rounded box, which by itself takes probably around 10 lines of code. So we will need to copy and paste it into 2 positions in order to do the differentiation between the models. And remember the oath, you do not copy and paste code again. What? You did it once, you regretted it, so now we try to move on. So what's the programmer's solution for not copy and pasting code? If you need the same functionality in 2 different places, you obviously create a function. In OpenSCAD, what you're looking for is actually called a module. So let's create a module called rounded box, which takes 2 parameters, our corner radius and size. And inside it, we put all the code that we have used to create this box as a standalone version. And this whole thing is a definition of a rounded box. And now in order to use it, we can just call rounded box, provide the radius, provide the size, and off we go. We have a ready working model. And here you may also notice that I used named arguments. This is an option, it's not a must. In OpenSCAD, you can both use either named or unnamed parameters based on the positions, so whichever notion is more suitable for you. So now we shift from our original simple box into the rounded box with just changing the name of the module that we are using. Instead of cube, we are using rounded box now, and we're good to go. But where's the definition of the rounded box? Well, it turns out that you can actually put it into a separate file. So we can have a file which defines how the module looks like, and then you can use it in other modules. So this way you can easily create a common code that you will share between different models that you are designing. And again, just for convenience, we create a variable, a constant of value of 8 for a radius that we'll use throughout the boxes. And that's it. That's ready to go, rounded box. And from this point on, actually, it's not really that far to create something like this. With additional loops for doing cut-ins for ventilation, you can actually easily design your own box, which suits perfectly your actual project that you're working on. And some people say that actually enclosures are the killer apps of 3D printing. So you can design any enclosure whatsoever, which matches perfectly what you are doing, and exposing only the ports of the board that you are actually using, which is great. You no longer need to do any custom enclosures that are not repeatable. You can have a model and you can share it with friends and they can reproduce your results. So we also mentioned at the very beginning that OpenSCAD actually has a logo which is itself designed in OpenSCAD. So maybe let's try to reproduce it. So first, we will define some radius, let's say 20 millimeters, and we'll define a sphere of radius equal to our constant value. But you can immediately see that even though we are not doing anything, we just declared a sphere and a difference for it, it's actually kind of clunky. It's not really as beautiful as the cube that we have seen previously. And that's because of the defaults. By default, the model resolution is fairly small. But you can easily increase it with $FN parameter, where you can assign a different value. You can increase the detail level of the model just by changing that value. But of course, the caveat is that the higher value is, the more precise the model gets, but on the other hand, it also takes more time to compute. So it will take far longer time to actually generate a model which is very, very fine-grained. And in practice, you actually need to have some sort of a balance, because you obviously won't get infinite precision, but on the other hand, the printer itself also has a limit. So it will not produce infinitely precise model. So actually, in practice, this is application dependent. So I often use very different values for instance, for small holes that should have tight fit for a screw, and something else for a part of a sphere, for instance, that should look beautiful when printed and should not have visible edges. So it's basically up to you at the specification. For the purpose of just recreating a logo, value of 150 fits perfectly. So now let's try to subtract our cylinder. So we'll define a helper variable for height, which will be 2 and 5 times radius. Twice the radius is actually the height of the sphere, and the additional extra half is just to make sure that the cylinder actually stands out from our sphere. So we create the cylinder with these parameters. And we actually also need to translate it down a little bit, and exactly by half of the height. Why is that? This goes again to the point where are the center of all the elements in OpenSCAD. In case of a cube, the corner of the cube is in 0.000, so it actually grows outwards. In case of a sphere, actually a center of a sphere is located by default in a 0.000. But in case of a cylinder, the base of the cylinder is in a 0.00, so it's basically OX, OY plane, and it grows upwards. So in order to make sure it's centered, you actually need to offset it by the height, half of the height. And this is a very typical thing to remember for different objects in order to subtract them efficiently. Now, let's try to do the same thing for OY. So again, we create a cylinder, we translate it. So this is actually a copy and paste of the code previously. And there is something new now. There is a rotation. So rotation takes one argument, and this argument is a rotation angles across all 3 axes, so OX, OY, and OZ. So here, what we are doing, we have a cylinder which is upward, and now by OX axis, we shift it 90 degrees. So effectively, it's now in a lying position. So this whole thing, rotation applies to translation applies to cylinder, and we mark it as a debug part so that we can actually see the cylinder, and we end up with what we see on the screen. Now, let's do something similar for OX axis. So we want to have a cylinder across this axis. And this is, again, basically copy and paste code from the previous axis. The only difference is that instead of rotating through OX, we are rotating through OY axis, so that's lying in a different direction. But aside from this, that's it. And of course, last step, we need to mark this one specific cylinder that we wanted to have in order to be an exact match for the OpenSCAD logo. We could, of course, play out a little bit with a correct angle of taking a preview, but technically speaking, we're good. But that's not how you would design a real object. This is something we wanted to reproduce as precise as possible. But in real world, you would probably want not to duplicate the code again, right? So the cylinder in translation, okay, that's no-brainer. This has to be done this way. But the rotation itself can actually be parameterized. So again, the rot value can be a part of the for loop. So we can iterate over vector of vectors. So effectively, rot will get 0, 0, 0, 19, 0, 0, or 0, 19, 0 as 3 distinct parameters. So this loop will actually create 3 objects. So effectively, 3 cylinders rotated in the right directions. So we end up with the model as OpenSCAD is designing. So the only reason we originally started with this copy and pasting code is because it's just a little bit more convenient to mark this one particular cylinder that we want to highlight. But in a real object where actually this highlighting doesn't really matter because it doesn't change the output of the print, we would actually go with the for loop. So that's the technique, the way to move forward here. Okay. So you might be asking yourself, okay, so I'm an expert now, right? I know all the OpenSCAD. Well, of course not. We barely scratched the surface. OpenSCAD is really huge. It has a lot of capabilities, a lot of built-in modules, a lot of functions that can compute math values. So you can create really complex shapes in a decent amount of code. What I have shown you is just the basics. So you can think of it by a 20-80 rules. So with a 20% of knowledge, you can actually solve 80% of the problems. And this is actually the great starting point. And to be honest, my first years with OpenSCAD were basically what I have just shown you. So this was like a 90, maybe 95% of my OpenSCAD knowledge, and I managed to live with it for a couple of years. And only recently, I actually started to create shapes which were so complex that the techniques that I showed previously were not enough, and I actually needed something more sophisticated. But if you're designing enclosures for most of the time, this will probably solve 99% of all the cases that you really need in practice. So what are the gains of using the OpenSCAD? So first of all, we finally have a source code for our model, not some binary in some proprietary closed source system. We have a source code. And when we have a source code, we can actually put it in a version control system like Git. So from that point on, we can apply our usual workflow. So we can do a code differentiation. So before committing, we can actually check which parameters have we changed and double check if we actually if we do not try to commit some temporary value that we just changed for a moment for the purpose of debugging, for instance. Same goes for working in the teams. You can now have a pull request, merge requests, and people can do code review. So you do not really need to rely on your friends' words that they have done the right thing. You can actually check and review which lines were changed and how. Which is awesome. Of course, you can also do branching and merging. So now everyone can work on their own branch and then merge into my development branch when they're ready. So what it means, you can also have a continuous integration running. And for each pull request, it can actually build your model. It can also generate previews. Generation of previews is awesome for documentation purposes, because now you can have a model which you generate a preview for and put it automatically inside generated documentation. So you do not need to do any print screen or word descriptions of the model on your own. It's just automatically updates with the code. And this is really powerful tool for documenting what you're working on. And in fact, this is also how I generated the previews that you have seen next to the source code in my previous slides. This was exactly it. The source code was actually compiled in OpenSCAD and generated preview. So what you are looking for is a source code and the automatically generated preview. And this is how the slides were made here. Another things that you can use from your regular tool set of programmers are techniques for reusing code. So we already learned how to use modules in order not to duplicate, not to copy and paste the code around. You can avoid hard codes by providing constant values that you use later on. You can have a modularization by moving a modules or a constant values into a separate files, which you can then use or include inside your modules. And you can play with encapsulation, but even though the OpenSCAD doesn't really support encapsulation on its own, you can have a convention, for instance, like a trailing underscore for a module name or a constant name in order to signal that this is something internal to this file and you should not use it outside of it. So there are ways to go around this as well. So let's see where we are in our workflow. So we have a CAD model, that's great, but we actually need something that we can later on try to send to the printer. So we need to have the STL file, so this intermediate representation. In order to do so, we need to generate STL out of the model, which is like super simple. We just call OpenSCAD from command line. We define what is the output name, the output file name, and what is the input, the source code that we would like to quote unquote compile, right? And this is really as simple as stating that trees don't move, right? So this is a very simple command and it does exactly what it needs, and you can actually script it to automate it. You can actually go even one step further, and you can define that OpenSCAD should be really picky about warnings and make them a hard stop for a compilation. You can enable extra checks for parameters or parameter ranges, which makes even more issues pop up during the compilation stage. So exactly as you do in a normal program. And with this, the compilation warnings shall not ever pass through, which is great, because what it actually means from our perspective is that OpenSCAD is actually our compiler, a part of our SDK, that we are now using to create objects that we will later on 3D print. Now, let's talk a little bit about slicing. So if you remember our pipeline, we now have the STL, but what we really need is the G-code, so something that we can physically send to the 3D printer to do the printing. And the process of generating G-code is called slicing. And the name is actually very descriptive here, because it is literally means take the model, slice it into pieces, horizontal pieces, and for each piece, try to generate the moves of the head in such a way that you will end up with a physical 3D objects made out of plastic. And of course, there are tools which does exactly that. So very common solution is a Slick 3R. I know it's stylized so that it's pronounced slicer, but there is a little bit of a problem with that name because slicer is also a name of a whole class of tools. It's like a car versus a particular brand of the car. So just to make sure we distinguish these two, I will say slicer whenever I mean any tool that does the slicing, and I will say Slick 3R when I am talking about this particular slicer, just to avoid confusion. There's also an open source fork of Slick 3R, which is called Prusa Slicer. This is actually very heavily developed at this point, so there is a really good chance that this will actually become a mainstream. There is also a Cura, which is a very common tool originating from the Ultimaker, one of the very well-known producers of 3D printers. And also there is a Simplify 3D, which is actually a commercial slicer, which used to be outstanding, but actually nowadays most open source slicer also have features in which are present in Simplify 3D. So it's actually losing a bit of momentum here. So from that point on, when I will be talking about slicer, I will actually be talking about Slick 3R. Even though I personally actually plan to switch to Prusa Slicer, and I'm already giving it a shot in some of the projects, I have the most experience with Slick 3R. So for the sake of this presentation and talking about it, I will actually focus on that. But the good news is that if you decide to use Prusa Slicer as well, it's very similar, because Prusa Slicer is a fork of a Slick 3R. It actually shares a lot of parameters, configurations. The look and feel of the graphical interface is also similar. So you should be really good. The switch should be really simple. So let's try a command line switch for generating the G-code. So we call a Slick 3R, we load a configuration, again, define the output name, and define the STL, the model that we would like to slice. And that's it. But you may actually scratch your head, okay, but what's the config thing? Like, where the hell do I get it from? And actually, it's, again, very simple. You can ask Slick 3R to generate the default config for you, and then you can edit it with your favorite text editor. But there is a little catch. Like, if you look into the config, it's actually, this is exactly the default config generated on my machine. It's around 200 options, and some of these options could easily make a full-blown lightning talk, and some of them can actually make a full 1-hour talk just to explain how it works, what it does, and how to optimize it for your particular printer. So there are things which are really not that straightforward. There are nice things in Prusa Slicer, for instance. For each of these options, when you enable Slicer in a graphical mode, you will get a dot next to each option. So you will get a green dot for something which is aimed for beginners. You will get an orange dot for something which is for experienced users, so the advanced option. And the last is a red dot, which is only for experts. So unless you have a lot of experience and you're absolutely sure what you're doing, you should probably not touch these values. So this helps. Another good news is actually that slicers nowadays provide really decent defaults. So if you select your printer type and you select the filament type, the plastic type that you want to print in, the default configurations will probably be 99% okay for your case. And if you're just beginning, they will probably do just fine, and you can just use it off the shelf. Okay, but we were talking a lot about this slicing, but we still do not know what's the output. So you may ask, okay, but just show us the output. And the output looks pretty much like this. So here we have 2 columns of commands, which at the first glance will look a little bit like assembly. And in fact, this is kind of an assembly for 3D printing. So each line defines a command for different purposes. From the top, we can see some setting temperatures, moving axes, for instance, changing the type of coordinates or extrusion speeds and so on and so forth. And finally, we reach the G1 command, which basically goes down through 99.9% of the file. And this G1 command is actually move the head and extrude along the way. So this is like the most important thing in the whole universe. But there is a thing about it. The G-codes are actually very long. So what you see here is probably around 30-40 lines of some random G-code that I just grabbed out of one of the projects. But the truth is that real files, at least for the models I was recently playing with, was on average around 200,000 lines of the code. So even though the file is perfectly human readable, it's an ASCII text, it's definitely not meant to be read by humans. So in order to see what is going on here, there are tools which can generate a preview for you. For instance, inside the slicer, if you enable it in GUI mode, you can actually have a look into it. There are also standalone tools. My personal favorite is YAGV, yet another G-code viewer, which does exactly that. It visualizes all the commands from the G-code and show how it looks like layer by layer, including all the heads move when the plastic is not extruded. And it shows you the overlay, which is very nice and very convenient to use. There are also some tools which are available online, so you can actually upload your G-code file onto a web page, and it generates a preview for you. So that's also an option. And why is this important? Because when you have a G-code, it's a sharp eye time, because the devil is in the details. And it turns out that sometimes, just by looking at this, how slicing resulted, you will actually learn a lot of interesting things. For instance, you just forgot to enable support structures, and your print will just collapse in the middle. Or maybe you actually enabled supporting even though you didn't wanted support to be there, because it will be hard to remove, and you know that you can print without in this particular configuration. Other things are actually bugs. I recently reported to both Slick3R and Prusa Slicer teams that there is a problem for certain types of geometries and certain infill settings. Instead of getting a proper infill inside of the solid object, you actually get an empty infill. So if you print the top layers on top of it, it will just collapse. So it will effectively break your print. Another common thing is about the details. So sometimes when you have very fine detail elements on the print, which is on the edge or below the print resolution of your printer, you can actually get these details lost. So we can end up with a hole in the model, or something which was really important for you just missing. So it's really good to spend a minute or two, literally, to go through the process and just see if everything went correctly before you actually start printing. Because when we try to estimate the time of the print, you need to know one thing. FDM printing is slow, like really slow. Generally, 3D printing is slow, and FDM 3D printing is like totally slowest thing on the earth, I would say. Just to give you some example, I brought with me a little cube. This is a calibration cube with marked X, Y, and Z axis, and this is precisely 1 cubic centimeter of filament. And this thing printed for like 45 minutes, this little thing. So we can imagine that any bigger printer will actually take even longer. So this is a slow process. So it's really good to invest upfront. And also, it's good to know how long will it actually take, right? So we know this will take long, but how long? Is it like long an hour or long a day or maybe long a week, right? My personal record is a print that fell short of 5 days of printing. So that's a lot of time. But the good news is that we have G-code at this stage, right? So we already know each and every move of a head of the printer throughout the entire print. So we would say, okay, that's great, so let's use it. And thankfully, there is a tool which does exactly that. It's called G-coder. On my Linux distribution, this is a part of a print run package. So we can just call it with Python, provide a parameter of a G-code file to analyze, and you get output which looks something like this. So there are some basic pieces of information regarding the dimensions of the cube inside which the model will print, an amount of filament that needs to be used, and the very last line is estimated duration, and this is something we are looking for. So here we have nearly 6 hours, short like 1.5 minutes, right? So you might say, okay, that's great. So we now have the exact amount of time, so I can just enable a stopwatch and see how precise it is. And this is where dragons lie. The problem is that even though the G-code defines all of the head moves, there are certain things which G-code is absolutely unaware of. Some of these are simple things, like for instance, heating time of your heat bed, of your extrusion, of a hot end of your printer. So this is something you cannot tell up front because this can actually depend on the environment, like for instance, what's the room temperature. There are even more important things, like things in physics do not happen at once. If you want to have something, some physical object moving at a certain speed, it actually needs to speed up, move at the speed, and then slow down. So if you have some short movements, you will actually be speeding up and just slowing down without actually going with this maximum speed whatsoever. So the firmwares of the printer typically are aware of this fact and are actually compensating. So it's not like the printer is blindly executing the G-code. There is a little bit of logic behind the scenes, and this can actually skew up your results a little bit. So you need to keep in mind that what you get out of the G-coder is actually a lower bound of the print time. In practice, this really depends on the printer. My printer is actually kind of slow one. So in my experience, it's usually between 100 and 150% of the time provided by the G-coder, and how much will actually take depends on the model type. So if there are a lot of short movements, I know that this will actually, this acceleration, deceleration thing will affect me greatly. So this is where I can actually get up to 1.5 times of the original estimation. If the print is simple, there are a lot of stride movements, I know that this will actually be very close to the optimal value that I have defined. So that's good, but you need to keep in mind. And this is, you may say, okay, if something has a 50% chance of missing the correct value, is it of any use? And I say, yes, absolutely. There is a difference if thing is going to take 10 hours or 10 days, for instance, right? Is it going to take an hour, or is it going to print overnight? So for this kind of things, for planning how long the printer will work and when to finish, this is actually a really incredible, important tool. So please use it. Just remember to take the results with a bit of grain of the salt. Okay. So now let's talk a little bit about the pipeline. So we already know that we want to automate things, right? We're software engineers. Our mindset is just designed for automation. And when automation comes in play, we want to have repeatability. And let's raise the bar even a bit higher and go towards reproducible builds. We're software engineers, so we basically know what reproducible build is. But just to make sure everyone's on the same page here, let me quote Wikipedia. Reproducible builds, also known as deterministic compilation, is a process of compiling software which ensures the resulting binary can be reproduced. Simple code compiled using deterministic compilation will always output the same binary. So, long story short, instead of instead of having build results which just happen to be the value that we computed at this particular point, if we have a reproducible builds, it doesn't matter if I build now or in 3 years' time, we will actually guarantee to get the same binary result each and every time. So if you look from this repeatability and automation point of view, we actually have pretty much all the bricks in place. So now let's try to glue them together. Let's try to make it happen. And by make, I mean GNU make. So this is an example makefile, which is actually fully working and functional automation for building the whole pipeline. So starting with the model and ending up with the G code. So of course, GNU make is quite a complex tool, and we definitely have no time to go into details here. So instead, I will just give you a glimpse so that you can understand the basics of what is going on in this particular piece of code. So first, we list all the SCAD files, so the source files, and write it into SCAD's variable. Then we define the file names of all the G codes. So basically, we take all the names of the SCAD files and change extension to the G code so that we now know which files we are looking for. And we define a target all, which will be the default one, and it depends on all the G codes. So it basically tells make, please generate all the G codes. Now, how the make knows how to make a G codes? Well, we just tell it. So we tell that STL can be created out of the SCAD, and the SCAD file can be pre-computed into the STL using following OpenSCAD command. And aside from obvious parts of defining output and input, there is also an interesting thing in the middle. -D tells OpenSCAD to generate the dependencies files. So it's something similar to GCC's -MD flag, which defines the dependencies for files in terms of includes. And a similar thing can be done for OpenSCAD, and you can this way track the dependencies. So if you are doing then incremental builds and just changing some of the files, some models, the makefile will now know how which files need to be rebuilt in order to get correct final results. So that's great. Now, the G code itself can be generated out of the STL file. And for this, we know the slick3r will do the trick for us. The config we just put in the same directory. Now, we also generate a dummy target called time, which depends on all the G codes. And for all the G codes, it runs a G coder with the file name. So this will effectively output printing time from the G coder for each and every model that we want to print. Then, of course, the usual clean target, just to make sure we get rid of everything that we have generated. So we remove the dependencies, the STLs, and the G codes. So we are basically back to clean repository. And the last but not least, we include all the dependencies files if they are there. So if there are no dependencies, we build for the first time, nothing happens. But if we do incremental builds, this is the line which will make sure that make is actually aware of dependencies between our SCAD files, source codes. So the usage is fairly simple. Let's create some 2 dummy SCAD files. Each of them will create a cube of a given size. And then we just call make. Make by default will call an all target here. So all the G codes will be created. Then we can call make time. And we get all the timings for printing. And we have actually the models and the time. So we are ready to print. And this is actually something totally awesome from my perspective, because it means in 12 lines of code, we can actually get a fully automated and working pipeline for working with source codes to generate the actual G codes for the printer. But of course, there is one catch. We talked about reproducible builds, and our SDK can actually change. If we run the same commands with the same makefile, in 2 years' time from now, we'll probably have a newer version of OpenSCAD, we'll have a newer version of slick3r, and we will effectively get a different result out of it. So in order to stabilize SDK, we will use Docker. So we'll try to containerize our whole build. And this can again be done simply with a short Docker file. So we are using Debian 11 as a base. Then we say to install additional packages. And the 6 core packages that we list here is actually all that is needed to make sure that our makefile is actually working. Now, in order to use it, we need to build the SDK. Then we can run a container using the image that we have just created, run it as a current user, and use the SDK which has been built. And we get an interactive prompt where we can type in the commands. So we can type make, all time, clean, or any other targets that we want. And with this step, we actually have SDK fixed in time as well. So now we have fully automated and reproducible builds for our 3D printing. So if you have used Docker in the past, That's great. The last 2 slides were absolutely easy for you, and it was a breeze. But actually, if you have never used Docker, I have a good news for you, because right after this talk, there will be a Docker Loves C++ talk, and where Piotr and Adrian will explain you how you can use Docker to create SDKs for C++. And actually, like 90% of this knowledge will also be applicable here. So with these 2 talks combined, you will understand every single bit of automation and repeatability and reproducibility that I'm talking here today. So we have automation, we have repeatability, so we're all done, right? Well, of course, in real life, one size doesn't really fit all, usually, and the same goes for 3D printing. And if you start using this pipeline, which actually is a pipeline which I originally created when I first started my adventure with 3D printing, something like half a decade ago, maybe a bit longer, but you will quickly realize that you need to have some points where you can variate things. So, for instance, you will print with different materials like PLA, PTG, TPU, and others. They require different temperatures, different print speeds, and this needs to be taken into account. Another common thing is printing for different properties. So you can have a draft print where you are just interested in rough object overview, and you're just interested in getting the print as fast as possible. You can have a pretty print where you are going into the fine details, because this is something like a sculpture that is supposed to look pretty. You can print for strength, so for something that will actually work mechanically. I very often do waterproof printing, so something that shall not leak in or out water. And all these profiles actually have conflicting interests. So different parameters need to have different values to make things work. And there are other more nuanced details that you will probably also find along the way. So in order to kind of stabilize it, I've created a 3D printing SDK project, link below and a QR code if you want to check it now, which basically provides all the basic functionality here. So it has a Dockerized SDK, it supports both OpenSCAD and raw STL files, so if you just download an STL that you would like to use as a part of your project, then you can also include it, no problem here. It supports multiple filaments, it has different build modes, so for instance, this waterproof versus having a fast draft print, and so on. And it also offers extensible interface, so it's fairly easy for you to actually add the new filaments or new build modes into the system. Okay, so we are slowly approaching the end. So let's quickly summarize what we have learned today. So first we did a little bit of an introduction into the 3D printing so that we have common base ground where we are. Then we learned some basics of OpenSCAD and slicing concept so that we know how to work with these tools, at least on a basic level, and how to automate it. We also estimated the print time, and even though the estimation is not perfect, it's actually giving us really good insights into what to expect. And last but not least, we automated all of this in order to have reproducible builds each and every time. Now, what should be the next steps? Well, I would highly recommend you go into Mastering OpenSCAD book, which is an open source book. You can read it online for free, or you can order a paperback version from Amazon, I believe, which goes through 10 example projects, each of them showing different techniques in OpenSCAD, which you can actually apply. So this is actually a great boost of OpenSCAD knowledge, showing a lot of tricks and techniques how to make the code readable and how to make it compact and yet solve complex problems. So I highly recommend you go through this. Now, there is a knowledge bootstrap, so there are a lot of links on the internet. When I was starting with 3D printing, there was barely anything aimed at beginners, but nowadays it's not the case. There are a lot of things, so I provide you some links. If you can now do a print screen and just go through the links offline. And if you want to wait after the conference, these materials will also be available, so you can then click through them. But the long story short is the internet is full of really quality pieces of information nowadays, starting from beginners going to advanced users. So pretty much anything you need to know is out there at the reach of your search engine. Okay, so if you want to do print screen, please do it now. I'm changing slide in 3, 2, 1, and it's gone. Okay, so thank you very much for your attention. That will be all from me. I hope you found this talk interesting, and I sure hope that you will actually try it out at home, because, remember, it's always good to try out new things. Thank you very much, and enjoy the rest of the conference.
This was Bartosz Szurgot talking about 3D printing. Don't forget about our virtual escape room. Check our website right after the conference. Hackdive is waiting. Welcome back. This is Code Dive, and I'd like to introduce our duo of speakers, Piotr Gaczkowski and Adrian Ostrowski. Piotr is a music and automation enthusiast. He's focused on efficiency and effectiveness. Experienced in management, programming, and DevOps, he enjoys building simple solutions for complex human problems. Occasionally, he writes for doomhammer.info. Piotr speaks about himself in the third person when required. You'll never find him without headphones, very rarely without sunglasses. Adrian is a modern C++ enthusiast interested in the development of both the C++ language itself and the high-quality code written in it. He's a lifelong learner, always eager to share his knowledge. Recently, he poured it into his latest book, Software Architecture with C++. His past projects range from parallel computing through fiber networking to working on a commodity exchanges trading system. Currently, he's one of the architects of Intel and Habana's integration with machine learning frameworks. In his previous life, Adrian promoted music bands, flew a glider, and sailed on the Baltic Sea. And they will both be talking about Docker and love and C++. So, Piotr, Adrian, glide forward.
Hello and welcome to our session about Docker and C++. My name is Adrian Ostrowski. I'm a C++ developer for almost a decade, and in my spare time I like to try various things like sailing, for instance. Recently.
And my name is Piotr Gaczkowski. I've been using C++ professionally for over a decade now, as a hobby even longer. Other than that, I'm also working with a lot of other stuff, web technologies, Python, so I have a pretty diverse background in that. And if you would like to talk about things such as music, books, parkour, or whatever, you can just catch me during the conference, and I'll be happy to talk about it as well.
Okay, so let's move to our agenda for today. We'll start with some rationale why even bother using Docker with C++. I hope you'll see that there's quite a few reasons for that. Then we'll mention how to use CMake with C++ code. Then we'll switch to Docker and see how to consume and produce packages. And after that, we will marry those two tools. After this, we will say a few words about multi-stage builds and running or doing other things with containers, like debugging them, managing toolchains, running external services in containers or using containers, and then composing multiple containers together. And last but not least, Piotr will show you how to use Docker in your CI/CD pipelines. So that's what we have for you today. It's quite a few items. So let's start with the first part, which I will lead, and let's go to why actually should we use Docker with C++. So one of the reasons is that you can actually run your code everywhere you want with Docker. It's very easy, and you don't need to bother with many environmental factors that you usually will stumble upon when you're not using containers. If you don't care about running code but playing with tools or trying out tool chains or running those tool chains in various environments, containers can really help you a lot and make your life much easier also. Another way or another thing that's easier is distributing software. So once you build your code and placed it in a container, it's pretty easy to ship it to wherever you want. Also, if your deployment or development relies on running various services, then it's pretty simple to run them using containers. It's much easier than it would be if you would need to install each service one by one and then run it. And it can be pretty complex, especially if you need to set this environment multiple times. Also, speaking about environment, if you want to have the same environment on developer VMs and in continuous integration or other environments, containers are a great tool that can help you with this. And last but not least, if you want to have a nice way to test how the production environment would work on your box or any other system set of machines, it's easy to deploy or produce a production environment using containers. So I think those are really lots of reasons to use Docker with C++, and you should definitely try to introduce Docker into your workflow if you haven't already. Okay, so let's now do a short recap about building C++ code. Before we can run it, we should build it. So actually, let's start simple. So this is CMake, and a simple target in CMake can be defined as follows. So basically, you take some sources, like a main file, you create an executable with a given name and specify the sources for it. Then you can set some features that you want to use. You can pass some libraries that you want to link into. CMake will automatically propagate features like target properties or include directories. Having all of that done, you can also set some compile flags or other properties. So once you have the simple target, you can not only build it, you can also install it. So installing using CMake is possible and recommended. So you can actually specify the list of targets you want to install. Also, you can install header files, licenses, many other types of resources. Also, you can use CMake to create you config files or CMake target files, so that when you write find package, those can be picked up. And once installation is in place, you can use a part of CMake called cpack, and it's a pretty easy way to create packages. So you basically just need to set a bunch of variables like the outer information, maybe some versioning, some description of the package, and you're good to go. You can create packages for many different formats like NCIS packages. Here you have a Debian package. There are also pretty easy ways to create RPM packages using cpack. So here all you need to do is set the generator to deb and then specify the dependencies for the Debian package. And then once you have done that, you can just ignore some files you don't want to package, and you're good to go. Once you include cpack, then CMake will know how to create your package. And then if you run cpack, then you will create this Debian file pretty effortlessly. If you want, you can also have a CMake target for packaging. So here you have a package just to build us the Debian package. All it does is using a custom target in CMake. It calls cpack with -gdeb, which is just invoking the Debian package generator. And we can set a dependency so that each time we build our Debian package, we know that our customer executable was properly built. So that's for CMake. Now let's move to Docker. So for those of you who don't know Docker, it's an engine to run containers, and basically it's very lightweight. It helps to deal with lots of environment issues. It's supported on many OSs, Linux, Windows, macOS, you name it. And it really helps you to have better infrastructure, simpler code for your infrastructure with the cattle, not pets principle. So If you're not familiar with this principle, I recommend you get familiar with it. So here we have a pretty complex example of how to run Docker containers. Actually, in most cases, you only need to type docker run and then the image name. Here we want to play a bit, so we want it to be interactive. We want the container to get automatically removed once we stop playing with it. We can set environment variables like this foo equals bar here. We can forward some ports from the container to the host. Here we can forward the 8080 port. And also you can mount volumes. Here we mount a path on the host to a path in the container. And we also do it as a read-only directory. Finally, we specify the image and the revision of the image, which is in our case the latest one. Okay, so yeah, as I mentioned, those were commands to run the Docker. Here we also have a Docker file. This is another part that's very important to run a container or to build a container. Here we have a basic image, so we want the latest Ubuntu, then we can add some files to the container, we install some packages and also clean up, so the image is as thin as it can be. So we do it in one step because it will create us one run command will add one layer. So our goal here is to have this layer as lightweight as it can be. We also specify what command should be called when we run the container and if it should expose any ports on the host by default. Okay, so having said that, we can also use the package, the Debian package that we created using CMake. So here you can see that we actually are installing this customer Debian package, which we produced from CPAC, and this is from the Docker file. So we need to first build with the package with CPAC, then here in the Docker file we add it to the container, then we install it, and finally we remove the files that we added. So that's all you need to do. And if you want to build this container, basically the simplest way to do it is to just run docker build, give it a context, or in our case it's the current directory, and tag the image. So we say that this is just the latest image, and that's it. Okay, so you can also give it additional tags. You can have different file names in the same directory or in the same context. So if you're building multiple containers, this can really be helpful. Okay, so now that we have CMake and we have Docker, we would like to marry those two. So so at best, we would want us to have a target in CMake that will, when we build it with CMake, we will get a Docker container. So to have it, first we need to find the Docker executable. So we first do a find program command. We find the Docker executable. If it's not found, we can fail with an error. Once we have it, we can configure a Docker file. So in our case, we just copy it from the sources to the build directory so that we can run Docker from the build directory. And then we add a CMake target. Let's just call it Docker, and it will build us the image from the Docker file you saw. It will tag it using whatever name we want. Our application is named customer, so let's just name our container likewise. And the last line here adds a dependency so that each time we build the Docker container or the Docker target, we make sure that the customer deb package is already built. And this is it. This is all you need to do. Then you can just CMake build using CMake this Docker target, and you will get a container image. Okay, so that's for marrying CMake and Docker. Now let's say a few words about reproducible builds. So so when you have a container, but you build it using your developer's environment, in many cases, you can be in a situation when someone says that it works for me, but for someone else this doesn't really work. So what you want is you want to have the same building experience on all the machines. And to do it, you need to containerize the whole build instead of just creating a container from your CMake files. And you can do it, or Docker has a feature that can help you do it pretty easily. So this feature is called multi-phase builds or multi-stage builds. You can use it for basically any task that you want to invoke, so that you have several steps and you still want to have a thin or minimal size image. So the whole magic is that you use multiple from statements, so you have multiple base images and then do steps on each of them and gather results from all of them. So you can have one step for building, then another one to copy the results to some destination image. So in our case, the Docker file would look like this. So we have a builder, we name it build, we run our customer deb target so that our Debian package is created. Then we get another from statement, and this time it's Ubuntu, the latest Ubuntu. So we copy the Debian package we generated within the builder, and then we just install it as we did before. So this way we end up with containerized builds. And also Docker has this build kit feature. It's basically a new way to build containers. So you can use more tricks using build kit, like you can cache the results. In this example, the run command that was building our Debian package before now also mounts Ccache so that you can get a faster build. And if you want to build your Docker container using build kit, you need to enable it and then run the build as usual. So that does it for build kit. Also, since you're already building and working in containers, you probably also want to debug your containers. So there's a way to do it, and the trick is to run GDB server from within the container, expose the proper ports, and then basically connect to the GDB server from the host. And you can do it by creating a Docker file. We base on the image that we just produced, and we basically just install the GDB server there. You can configure it as you like, and you're good to go. So I think that does it for my part of the presentation, and now I would like to welcome Piotr to the stage to tell you a bit about managing toolchains.
Hello again. Yes, managing toolchains. So Adrian already mentioned how to make sure that your build environment stays the same regardless of which machine are you building on. Historically, you may have seen different approaches to that problem. So for example, you may have received a pre-installed machine from IT, which has all the compilers, which has all the libraries necessary to build your code. Or you can have a VM image, which is kind of similar, but a bit easier to manage afterwards if you want to update something and distribute the updates to everybody concerned. Or you can go with change root images or container images. That's also fine. But whatever you do with any of these approaches, it has one slight problem that I'll mention shortly. Another way would be, of course, to use also, application images. Are there any other ways to manage the toolchains? Yeah, probably there are many more. I assume most of you has seen some homebrew stuff that's used for exactly this purpose. But the question is, you get the toolchain. It is pre-configured. It uses some version of GCC, for example. But then how do you upgrade it? How do you make sure that all the new versions of the compilers are there when they are needed? How to make sure that you have the fresh versions of libraries? This is one of the biggest challenges. And one way to handle that is to get familiar with Conan. I'm not sure if you know Conan already. If not, this is a good time to write it down and check things out, because Conan solves a lot of problems related to C++ dependency management. It's really, really cool in these regards. Mostly it works like cpan, PAP, npm, gem, the package managers known from interpreted languages. If you know them, then Conan is kind of similar. For example, in PAP, you have the requirements.txt file, which lists all the dependencies of your project. In Conan, you have the Conan file txt, which, lists the dependencies of your project. So that would be it. But since Conan deals with C++, of course, things are a bit more complicated, because in Python, you typically don't care about the OS architecture, the build target, the different ABIs, nothing like that concerns you. In C++ world, well, yeah, different compilers, different operating systems, different versions of ABI, different build targets, because you might be doing some cross-compilation. So usually this is the stuff that gives you headache whenever you want to build and configure your C++ project. With Conan, most of the headaches are already gone. So even if you are not convinced to use Docker after seeing this presentation, I think that it's at least good to check out Conan, because this could also help you. One of the big strengths of Conan, in my opinion, is that it allows you to install C++ libraries without super user permissions, or at least most of the time. There's some Conan libraries that still rely on native package managers, but most of the time you just install what you want locally in your home directory for the specific platform that you want, for the specific configuration, whatever. It doesn't require root permissions. It doesn't require asking anybody if you can bump the version of a library or whatever. You just change one tiny file, Conan file txt, and that's all. But you probably wonder, why am I telling you about Conan right now, since this is a presentation about Docker, right? Because you may imagine that people working at Conan might have quite a lot of work to do with getting all the binaries. Oh yes, I forgot to mention binaries. Whenever binaries are available for your architecture, Conan downloads the binaries, not the source distributions. But if you are on an unsupported platform, something custom, whatever, then you get the sources which are then built with your compiler. So whatever you do, you aren't left alone with Conan. And yes, in order to get those binaries built and put in the Conan repository, the main repository of Conan packages, they needed to build all those packages with different configurations. And you probably wonder, how did they manage to do it? And the answer to this question is that they've used, of course, Docker. And not only they used Docker, but they were also very nice to all of us who may be in a similar situation. So the Conan project provides some very nice base images on Docker Hub that we all can use. Why are they nice? They are pre-configured with the compilers, with the most common tools that we may want to use. All of it, you can select a version of the compiler as long as it's supported to whatever you like. And basically build your project with that. So different versions of GCC are supported. The last time I checked, 4.6 was the oldest one, and GCC 11 was the freshest one. It also supports different versions of CLang. Again, the last time I checked, from 3.8 to 10 were supported, but I assume by now the newer versions are also there. And this is actually a funny part. Visual Studio 14 and 15 images are also available, though they are not redistributable. So if you are on Windows and using Windows containers, you may want to try Visual Studio 14 or 15 images and play with your code. So other than different compilers, I've mentioned that different cross-compiling platforms are available and different toolchains are already there. So if you are targeting 64 Intel architecture, then you're set, because all the compilers running in the containers are 64-bit Intel architecture by default. But if you are targeting ARM v7, or maybe ARM v7 with hard float, or ARM v8 by any chance, there are cross-compilers already configured that you can just take with a simple Docker run and the name of the base image. So that's pretty cool, because again, historically, setting up cross-compilers and doing it properly took some time. It could be weeks even in some cases. Now, Docker run, and 2 minutes later, GCC is compiling stuff for your ARM device on your machine. That's very cool. Also, there are Android toolchains available for native development. So if you're an Android developer, it's worth checking that as well. Other cool features of Conan-based images, they are compatible with different CI/CD systems. I'll tell more about CI/CD systems later on. But some images are just pre-configured to act as JNLP slaves for use with Jenkins. So you just set up your Jenkins instance and run the JNLP Conan Docker images on all your build machines. And that's all. You probably don't need to do anything else, so no setup is necessary for Jenkins in this case. This is also a pretty cool feature, I would say. It's also possible to use with all the other container-based CI/CD systems. So Travis is mentioned here. Circle CI is as well supported. GitLab CI, GitHub Actions. Yeah, all the modern stuff that I can think of works with containers and thus can benefit from the Conan-based images. So if you are looking for good stuff to try on new compilers or different compilers, or try to cross-compile your application to new platforms, Con base images are the place to start. Oh yes, one caveat, these are only suitable for AMD 64 hosts, so they can only run on Linux AMD 64. But Linux AMD 64 is like the standard for containers, so if you are running containers on Windows, you are actually running Linux AMD 64. If you are running Docker on Mac, you are also typically running Linux AMD 64. So that should be cool. The exception is that Visual Studio containers, of course, only run on Docker for Windows. To be honest, I'm not entirely sure how these containers behave on newer Macs with the M1 chip, because these are ARM architecture. Haven't tested that yet. I'm curious to see how it works. But yeah, if you're running an Intel Mac or a Linux or Windows, then these containers are there for you to use. So yeah, I spent quite a lot of time already talking about these base images and all their virtues, about how to actually use them to build something with Docker. Don't be scared, this comment or these comments may look a bit daunting, but this is only because we want to pass a few arguments to the Docker engine. So we want to run a fresh container, we want to remove it afterwards, that's the /rm. We want to run it interactively and with a TTI attached. And what we definitely want is that we want to have a volume with a cache to hold the Conan dependencies there. We don't want to download all the dependencies anew each time we rebuild our stuff. So we mount the local Conan GCC 10 volume as the home/conan/.conan directory inside the container that we want to run. Another volume that we want to run is the current working directory, and we want to mount it as /home/conan/src, and this will of course hold our sources. We also want to set the working directory to the Docker build subdirectory of source. And that's it for container configuration. Then we specify that we want to use the conan.io/gcc10 image. And we run, first of all, conan install. The second line here is identical when it comes to Docker configuration, but this time we are running cmake to configure our project. And finally, in the last step, we want to build it. So yeah, a lot of scary stuff with Docker configuration, but other than that, we run conan install, we run cmake to configure, and cmake build to build our stuff. That's cool, but we can also make it a bit cooler because we can run all the three steps as a single shell script. And to do that, we use the same docker run, /rm, yada, 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 yada invocation. But as a command to be run inside the container, we are running bash, specifying the script conan install, &&cmake, &&cmake build. So this will run all the three stages as a single step in a single container. If we would like to use it from the command line, we would probably go a step further and, for example, configure an alias for conan.io gcc10 that does the conan, docker run yada 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 conan gcc10 for us. So then we can call from our shell conan.io gcc10 conan install, conan.io gcc10 cmake, conan.io gcc10 cmake /build. This is a bit more friendly than the previous invocation with the entire stuff there. But yeah, we can also try different things. Typically, if you are running this toolchain, you may also be already interested in creating containers, so you wouldn't be doing all those Docker run stuff, but instead you will write a proper Docker file, ideally using BuildKit to handle the Conan cache, the C cache, all the other stuff that might be interesting there. But let's stay in this like manual way for a moment and imagine that at some point in time we figure out that the feature that we want to use is not available in GCC 10 and we really need it. This is like something that would totally improve our code. So what do we do? Normally, if you have a machine with all the stuff pre-installed from IT, you need to issue a ticket saying that please upgrade GCC 11 everywhere, so that the entire organization will have to update all their stuff to GCC 11. But before this upgrade is possible, everything needs to be tested, so it takes time. It may take days, it may take weeks, it may take months or ages. I recall being in a project where we are using GCC 4.8, I guess, and we really wanted to touch GCC 5, like desperately. And there was a lot of talk about upgrading our toolchains to use GCC 5, but basically the team that was responsible for setting up our development environments always had other more pressing features to implement. So the compiler update was always postponed and we had no way to do it. If we are using Docker-based toolchains, then it is up to us to decide which version are we running. So if we want to upgrade the toolchain, we don't have to issue any tickets and waiting days, months, or ages. We just need to switch the GCC 10 part in our invocation to GCC 11. And that's that. Of course, we haven't used GCC 11 before, so Docker will download the container image to our local machine and then transparently execute it just the same way as it previously executed the GCC 10 compiler. So that's that. The only change is needed in the name of the image and the name of the volume to hold the cache, because Conan cache might be incompatible between GCC 10 and 11. Conan uses quite a good method to store different versions of dependencies, so that shouldn't be too much of a problem, but to stay on the safer side, you can just use a separate volume. So what's inside the image of the Conan base GCC images? Of course, a compiler with its toolchain, GCC LD, all that stuff, or Clang and all of their stuff. There's wget and curl, there's git and subversion, there's the assembler, make and ninja for build systems, package config for working with non-Conan based legacy packages, autotools, of course, because some of your dependencies may require autotools. There's the JFrog CLI. JFrog is a company behind the Conan, so if you want to upload the artifacts to JFrog, it's possible out of the box. Of course, there's Conan, of course, there's CMake. They're using pretty recent versions of both Conan and CMake, so you don't have to worry about that as well. There's Python installed, because some C++ projects aren't using CMake, but instead are using, for example, scones or WAF. Where suitable, there's the Android NDK as well. This is, of course, for the Android targets. And Conan profiles for cross compilers are also available if you choose to go with cross compiler Conan based image. So if you're targeting ARM machines, for example, everything will be pre-configured. Okay, but still something might be lacking. You might be using a different build system, for example, or you might rely on some other tool or library that is not already there. If that's the case, cool, this is Docker. You write your own Docker file, you install what you want, and you use this as your base image instead. So for example, we want to have the Qt5 with GCC 10. Cool. From Conan.io GCC 10, we run apt-get update, install Qt5, remove all the stuff that we don't need, and use this for a base image. Now, another cool trick with Docker is running external services. If your application uses something like Postgres, MySQL, Redis database, whatever external services, then typically you need to install them, configure them properly, and they're probably running all the time on your machine, wasting your resources. With Docker, you can start them whenever you need, close them when they are no longer needed, and that's also one command away. If you want to run Postgres, Docker run Postgres. If you want to configure the Postgres, you can type Docker run -e, that is for setting up environment variables, Postgres password, whatever, Postgres. This is also suitable for, as I've mentioned, Redis, Nginx, other types of databases, other types of caches, ICT scheduler, most of whatever else you need. So that makes things a bit easier. But you probably don't want to type all the time Docker run Nginx, Docker run Redis, Docker run Postgres, whatever, if you're running them all at the same time. Then you may want to use Docker Compose, which allows you to run anything and everything in one single command. This is another file, this time a YAML file, that has all the container configuration within it. It can set up and tear down the resources, manage the networking, manage volumes. And it's also possible to overwrite those values later on if you need them. So even if your services are really complex, Docker Compose is flexible enough to handle that. Here's an example of a Docker Compose file. We specify the versions of the file. We specify that we want to have Redis that is connected to the backend network. We want to have the Postgres database that is also connected to the backend network. And it has a persistent volume stored somewhere. And we also want to run our customer image that Adrian already told you a lot about, connected to both backend and frontend networks. That's that. Besides running several services in parallel, Docker Compose can be used for documenting one-off commands. So if you remember this long Docker run invocation to run the GCC compiler, this is something that we can handle with Docker Compose and also make checking different compilers side by side very easy. It can also be used to handle builds for different distros, easy cross-compilation, compilation against different versions of dependencies. A lot of these use cases can be handled with Docker Compose, either with overrides or with using some variables. So here's another example of how it looks like. We define two services, GCC 10 and GCC 11. GCC 10 is based on GCC 10 image. GCC 11 is based on GCC 11 image. If you look at it closely, it is exactly the same thing that I've used previously for the invocation. So I'm selecting an image, I'm mounting two volumes, I'm setting up a working directory, The only things that I don't do here is making sure Docker removes the container and attaching a TTY, because that's not needed here. And if I want to use it, I will call docker compose run gcc 10 and then go with our invocation. In my opinion, this YAML file is more readable than the previous shell alias, and it can be even more extensible. So the last part that I wanted to touch is CI/CD with Docker. I've already told you about Jenkins. Conan base images are pre-configured for that. Travis, Circle CI, GitLab CI, GitHub Actions, all of them are based on containers to some extent. So it is very easy to use the Conan base images there. I won't go into full examples, full details of how to configure the CI/CD pipeline for that. But if you have ever configured CI/CD pipeline, you may recall it is a lot of pain. And with these Conan base images, well, you want to have GCC 8 on GitLab CI? Sure, that's what you need to do. Select an image that it will run in, write the script, select which artifacts are to be kept. That's all. Then you write the necessary step that extends this previous configuration. And in this step, you may also overwrite some of the configuration parts. So you can overwrite image, you can overwrite the variables for the compilers. So instead of running with GCC 8, you are now running with GCC 10. Cool. With Circle CI, once again, you configure executors, you select the Conan.io GCC 10 image as a Docker executor, and then in the jobs definition, you select that the necessary job is executed on GCC 10, and it runs Conan install, cmake, cmake build. Cool. GitHub Actions, this requires a bit more typing, but it's also pretty easy if you've worked with GitHub Actions before. You can define a matrix of different Docker images that you want to build against. And then in the definitions, before you define steps, you select that you want to run inside a container that is related to the current Docker image from within the matrix. And as a step, it first checks out the project, then it sets up Python, because Conan is a Python thingy, so it needs the fresh Python version. We are selecting here 3.8 because that should be cool. And then once again, Conan install, cmake build. So some of the benefits of using Docker for building is that the same toolchain and dependencies are everywhere, and I mean it everywhere. With Adrian, we saw certain cases where the toolchain should have been exactly the same between the development machine and the CI/CD system, but for some reason it wasn't. And there were errors in the CI/CD process that couldn't be reproduced locally, all because it used native packages and not containers. So other than that, it is also very easy to change the configuration via a Docker file, and the entire configuration of your build system, of your development environment, of your CI/CD is documented inside this Docker file, which is also pretty big feature, I would say. So yeah, same toolchain locally on CI/CD everywhere. Easy to test new features. If you want to try a new compiler, new library, you modify the Docker file or the Docker compose, that's that. You can have massive parallel builds with different settings manageable from a single file. You don't need to think about how to install different versions of GCC side by side on a single machine. You don't care. You just run different containers, and they're all separated from each other. That's it. It is easy to distribute the images. You don't need to think about how to push those VMs to all the developers and how to make sure they're running the latest version. With Docker Hub, you just do Docker push the image anywhere, and whenever somebody is running Docker run, they're just downloading the fresh version. Definitely lower overhead than VMs. Containers are basically native speed or close to native speed because they are virtualized on an OS level, not on a hardware level. And yeah, Docker gives you power to the people because finally it is you, the developer, that can choose which library version, which compiler version you are running. And you are free to experiment without anybody else telling you that they don't have time to upgrade all the compilers. So this has been pretty long already. To sum it up, Docker is cool because you have same stuff on dev, CI, and production. You can get third-party stuff super easy. You can integrate stuff only with changes to the Docker Compose YAML file. You can try new stuff just by running Docker run. That's it. If you are hungry for more, Adrian will tell you a bit about our not that new but still quite recent book.
Yeah, I think it's like half a year on the market already. It was a bestseller in the C++ category. So if you want to learn more on Docker, on Conan, on building packaging, on designing software, even some C++20 features and various approaches to architecture, design patterns, architectural patterns, and more, feel free to buy it, to read it either on Pact or Amazon. If you already bought it, then we wanted to thank you. And I think that's all from our side. So if you have any questions, you can catch us either on the conference or later on using our handles. So I'd like to thank you, and I guess Piotr would like to thank you as well. So
yes, thank you very much for listening to us talk about Docker. I hope all this information would be useful to you, at least some of them, maybe not necessarily all, and I wish you a very good day. Enjoy the rest of the conference.
Piotr Gaczkowski and Adrian Ostrowski talking about Docker. Thank you so much for your insight. Don't forget about our virtual escape room. Check our website right after the conference. Hack Dive will be waiting. Hi again, let's continue, and our next speaker is Maciej Nowak. Now, Maciej started his adventure in professional software development over 10 years ago with .NET and a web browser. 6 years ago, he changed his career and currently works on flight software for satellites. Recently, Maciej has been part of the PWSat-2 operations team. PWSat-2 is a satellite built by a group of students at Warsaw University of Technology. In his spare time, he likes to watch Star Trek while playing with the cables connected to the microcontroller. Maciej, welcome to Code Dive.
Okay. Hello everyone. During this talk, I'm going to show you how we are using QEmu as a tool to aid us with development of flight software for Cortex-M embedded target. To give you a bit of context of background where I work for a company called KP Labs. It's a startup from Poland, from Gliwice, working in space industry. I'm part of the team that is responsible for developing flight software for embedded components. And most of developers in our team have previous experience in working with PWSat-2 flight software. We are working on software for onboard computer, and we're also part of the operations teams for the whole mission. Right now in KP Labs we are working on Oryx. It's an SDK for developing software for small onboard computers, targeting mostly bare metal devices. And beside Oryx we are working on two quite interesting projects. They are Intuition One, which is biggest project of our company. It's building our own hyperspectral Earth observation satellite. It will be launched at the end of next year, and Oryx is used there to build flight software for onboard computer that will govern whole mission. And also we are working on Antelope, which is an onboard computer for small satellites that can be programmed with Oryx as a base tool for developing software by end user. And Antelope will also have some machine learning capabilities with predictive maintenance. When we started working on Oryx a few years ago, we gave ourselves a bit of challenge how we can approach to our day-to-day development. So we wanted to know how close can we get to running our software on daily basis by every developer. How close can we get to running our software on target hardware when we don't have access to that hardware? Because problem with space components and with specialized electronics in general is that lead times are very long. Right now the problem is even worse due to chip shortage, but even few years back it was a pretty long time before we get first engineering model of our OBC for Intuition One. It was more than a year from start of the project to receiving first hardware model. And during that time we had to find some way how to work with our software to test it. But the only things we could use from hardware components were some development boards, but they were not really available or matching our target hardware. So we wanted to find some other way. Why not just work on desktop machines and compile everything there and hope for and finally compile it for ARM machine and hope it works? Well, we wanted to use single toolchain for all our development. So if there is some issue with compiler, like linker playing with us and removing needed symbols, we wanted to find that kind of issues early in the project, not in the late phases when fixing them could be a problem. We wanted to maintain the same memory constraints. So flash area that is read-only and has limited space, RAM memory that is limited, stack that can overflow other important parts of memory, or no heap, stuff like that. We wanted to stick to the same real-time operating system. We are using FreeRTOS for our projects, and we wanted to use this operating system for our multitasking capabilities, use its synchronization primitives, so we could catch all overflows or all deadlocks, problems with built-in functionalities. Also, we wanted to stick to the same interrupt model as in target hardware. So, for example, in RTOS, there are functions that can't be called from interrupts, but it's quite easy to, by mistake, call a non-interrupt save function from interrupt, and that usually leads to smaller or bigger disasters. So we wanted to prevent these kind of issues from happening. So how can we run bare metal ARM Cortex-M executable on our desktop machine? Well, we can run it directly, so we need some form of emulation. Luckily for us, the open source emulator, QEmu, has support for Cortex-M's machines, and it's customizable enough so we could use it for our needs. The first problem we hit is that Cortex-M support in QEmu is a bit limited. The only machines that are supported are a few off-the-shelf boards that are not matching our target hardware. Even our MCU is not modeled in QEmu in the way you could use it. So maybe we could write our own machine that will model our target hardware. But even if we are using exactly the same Cortex-M that is modeled inside QEmu, there is a problem with peripherals. Because in supported Cortex-Ms, and most of the machines that are in QEmu right now, the peripheral support is limited. Not every peripheral from every MCU is implemented, and even if it's implemented, there is no guarantee that will work exactly like the hardware counterpart. Of course, it is possible to write peripherals that will exactly match peripheral from real hardware, but it will require reverse engineering silicon and building code that is feature compatible and also bug compatible, so we could be sure that it works correctly. And without knowledge of how the peripheral is implemented in hardware, doing it in software is very, very hard. So while it's doable, it's not a very feasible solution. So we need to find some other way. How can we use QEmu and its emulation capabilities to work with our project? So we took a few steps back and looked how we are using peripherals in code. The code on the slide shows you very generic, a bit simplified code that handles different peripherals. This template works for most of the peripherals, and there are a few important things that we could use to model our solution. So the most important part of this code are two methods. There is doWork method and interrupt handler. The doWork method is called from some task. It receives two buffers, one with input data, let's say it's data that will be sent to some I2C device, and there is output buffer that will receive data that are sent back from this device. And inside the doWork method, we are preparing transfer. So this requires talking to some peripheral, setting up some flags, maybe setting up DMA transfer. At the end, we are sending input buffer into this peripheral. Then we are waiting on semaphore for peripheral to signal us that transfer was finished. After transfer is finished, we are reading back the response into output buffer. This semaphore that signals the transfer finish is unlocked from interrupt handler, and interrupt handler is is invoked by peripheral after finished transfer. So if we could provide some way to build very generic peripheral inside QEmu that will give us similar capability, but instead of talking over I2C device, it will talk to some other program running side by side with QEmu, we could implement different peripherals and model behavior of different buses in some, let's say, Python in some easy way, and provide a way for program running on emulated CPU to communicate with this program and use these simulated buses. Currently, QEmu supports two ways of for program running on emulated CPU to call something that is running on host machine. The first one is semi-hosting, and the other one is by using devices. Semi-hosting is part of ARM specification. It's a mechanism very similar to system calls known from big operating systems like Linux, Windows, but it's tailored to work on smaller devices like Cortex-Ms. It is using breakpoint instruction to interact with QEmu or with any debugger like JLink or OpenOCD. And when this breakpoint instruction is executed by CPU, in case of QEmu, there's some special callback that is invoked. The state of CPU is inspected, and specified operation is invoked. These operations are used by library called RDII-mon. It's part of newlib for ARM targets. That library implements I/O operations for target using semi-hosting calls. For example, we can use print functions to output something to standard output. We can also access files on host machine, which is useful because we can gather code coverage, for example, very easily, just by linking with gcov, or we can output unit test results. So very nice stuff. The downside is that semi-hosting implementation is very tightly integrated into QEmu. If you look through source code of QEmu, you will find single file with quite long switch, with cases for different operations, and each case handles inline each operation. There's really no mechanism to plug in our own system calls, our own operations. So we would have to modify the file to add our own operations. So you can imagine that maintaining it will be a nightmare. Also, if ARM will decide in a few years that, yeah, we need to add a few more operations to semi-hosting, probably there will be some conflicts with operation codes. So not really a nice thing for extensibility and custom operations. Also, semi-hosting is specific to ARM platforms. It was adapted recently in QEmu to support RISC-V, but if I'm correct, it is not part of the official specification. So this approach will work only for ARM machines, not for other targets that we might be working with. The other way to work with, to provide some communication with host machine is by using devices. QEmu is built around devices. It has a pretty extensive infrastructure for them. Most important, it's adding things to QEmu. It's not changing things already in QEmu, so it's really nice for extensibility and maintaining in long term. Devices can provide memory mapped I/O, so we can define memory region at specified base address. where writes and reads are handled by callback specified by us. So program running on emulated CPU writes some value to memory address. This memory is mapped to our device, and some callback registered with our device is invoked every time CPU writes something to that memory address. We can handle that write as we see fit. Also for reads, we can return the value that will be returned to CPU. This flow is very similar to how we are working with peripherals on real hardware. Also, most of the devices are using microcontrollers are using memory mapped I/O for peripherals. So the operation is very similar and matches what we see on hardware. Also, devices are architecture independent. There are some exceptions because working with interrupts is a bit of platform specific. But in general, memory mapped I/O works for every architecture. So if we write our device once, we can reuse it on different platforms. We started with prototype implementation of semi-hosting, but quickly switched to using devices, and that's the way we are working with QEmu right now. So once we implement some sort of device plugged into QEmu, we need to provide some way of the device to communicate with some process running along with QEmu, so we do not have to implement every bus and simulation of every device inside QEmu, because that will be not very easy to do. We wanted to move it to some other process. Of course, we could use bare TCP sockets for communication, but we wanted something more like message-based communication. So we decided to use a library called NanoMessage, which provides message-based communication with some communication patterns like request-reply or push-pull over TCP sockets or many different transport protocols. And the only thing we need to do is to push messages through it. NanoMessage is similar in usage to 0MQ. Actually, we started with 0MQ, but hit some issues with event loop integration inside QEmu. So we had to switch to less popular NanoMessage. But the idea behind that library is the same. So putting everything together, we have created something called external device interface, in short EDI. Each EDI provides us with single NanoMessage socket from one side, and on the other side it's mapping into emulated CPU address space. So we have program running inside QEmu on emulated CPU, it's executing instructions, and there are one or more EDI devices, each providing a single socket. Program can talk to these devices by writing and reading from memory. Operations invoked on this device are translated into NanoMessage operations. Messages are sent and received. On the other side of the socket, they are handled by a test host application that can be written in any technology. We are using Python for that purpose. And there is some code handling each socket. And one socket is, for example, for handling I2C devices. So there is a deconic of I2C transaction, dispatching into some device simulator. Simulator responds with data, performs some operation, and responds information back to QEmu. Similarly, we can work with SPI, UART, we can have dedicated logsync, many different peripherals. We don't have in QEmu as a built-in and ready peripheral, but we are using generic EDI to escape QEmu and emulate these peripherals in some other application. From the code point of view, EDI usage is just few operation. This is the same template of peripheral driver I shown you before. but this time it is adapted to use EDI. This time the initialize method is a bit more complicated because we have to set up the EDI socket. We are starting by setting connection type. For most of the peripherals, request reply pattern works best. Then we are connecting to specified URL. We are using mostly inter-process communication with named pipes because we can easily customize the name of the pipe to avoid conflicts on CA builds. After connecting, we are wiring EDI to interrupt. So every time EDI1 receives a message, interrupt number 12 inside CPU will be raised and our interrupt handler will be invoked. Inside the work method, there are very simple operations for sending message over EDI socket using write command. And whole buffer is just sent to socket. Then we are similar to a hardware driver. We are waiting for incoming message or to transfer to finish, and then we are reading message from the incoming messages queue. On the test cost side in Python, we are using pure nano message library to create socket, bind it to the same address as used in QEmu, and in background thread we have loop that handles all incoming messages by receiving each message, handling it accordingly to the protocol and peripherals. So, for example, dispatching to I2C the device simulator, some response is generated and sent back into QEmu, where it will unlock the semaphore and do work method and resume, and the program can continue. So this pattern works for I2C, SPI, UARTs, a lot of different peripherals. Because EDI wraps nano message socket, it exposes most of the operation from socket to emulated CPU in form of several commands. So you have connection management, things like setting connection type, connecting, binding, or disconnecting. Disconnecting is useful for restarting the CPU, but it's not really required, and we are not using it very often. We have message-related operations like writing and reading messages from input and output queues. We also support gutter-scatter operations, so you can build single message from several buffers in CPU address space. This is particularly useful for buses like I2C when you have to add some additional information to each request, like device address. So by providing gather operation, we don't have to copy all input buffer to some temporary buffer just to prepend few bytes. Or on the other side, combine several messages into a single operation. There are also a few more informational operations like querying the number of messages waiting in queue or size of the message at the head of queue. Memory mapped I/O exposed to CPU is just 5 registers. The command register is used to trigger specific operations. So by writing command code into it, you are triggering callback in QEmu. Pointer and size registers are used to describe buffer associated with executed command when it's required. Some operation does not require any buffer. Interrupt register is used to wire EDI with interrupt number that will be raised after receiving message. And ID register is just constant value that we can use to verify that QEmu is configured correctly. For gutter-scatter operation, there is helper structure, EDI message part, and we are just providing array of these structs to describe different part of messages. Inside QEmu, things are getting a bit more complicated. So typical flow of message is that program writes to EDI registers to trigger different operations. After write operation is triggered,
the message is read from CPU address space and put into outgoing message queue. Nano message is integrated into a QEmu event loop to avoid any threading issues. So when Nano message notifies us that it is ready to, the socket is ready to send next message, we are getting message from queue and sending it using Nano message. And when message is received, we are also notified. The message is received from socket, put into incoming message queue. If configured, interrupt is raised in the CPU, and CPU can access the incoming message queue by accessing EDI registers. What is important is that CPU is not waiting for a message to be sent. It's done asynchronously. The CPU is suspended only for the time that is required to copy buffer from CPU address space and put it into outgoing queue. We had to make some changes to QEmu. We started with creating Virt Cortex-M machine. It's a very simple machine. It's not modeled after any off-the-shelf board. It's just a simple CPU, and you can configure which Cortex-M CPU is used, ranging from Cortex-M0 to M33, and you can use any of CPU supported by QEmu. There are no peripherals by default. There is only a memory, both for flash and for data storage, and you can configure these sizes. Also, you can configure number of interrupts, so you can model something close that is close to the hardware, or more generic machine, for example, with lots of flash and lots of RAM to run unit tests. This is also useful. If you want to use EDI, you need to instruct QEmu to add KP EDI device, and single device provides you with single socket. Then you can map at a specified memory address. If you want to add many EDI devices at once, it's useful to use KP EDI group device, which creates just several devices one after another in memory. So very simple command line for running something under QEmu is on the slide. So we are using Virt Cortex-M machine with 2 megabytes of flash. We enabled semi-hosting, so you can use primitive debugging if something goes wrong. We are running up-elf image, and we are adding 20 EDI devices at their default base address. Right now we have support for EDI for 4 different architectures. This is mostly caused by the need to work with interrupt controller. So that's why the EDI is not very generic. But right now we can run it on Cortex-M, and that's the solution we are using in our projects right now. We have support for Cortex-R. We also had to create Virt Cortex-R machine. It is using generic interrupt controller v1 from ARM. It's working, but not in production use right now. We have support for Atmegas, so 8-bit machines from Atmel, for example, Arduino, and their EDI works with any machine already supported by QEmu, and this is this platform we are using in our projects. And recently, like a few weeks ago, we added support for Leon 3. It's a Spark V8 architecture used in space mission. It's a software from Geissler, but there is already a support for it for QEmu, and we just added QEmu for it, just added EDI for it. So right now we have capability to run our Cortex-M application in QEmu, communicate with some test host application, emulate different peripherals, different devices. But the real hardware does not provide us with EDI peripherals. That would be interesting, to be honest, to have Nano message built into silicon. So we need some way to switch our application from QEmu to hardware very easily. And to do so, we are applied the most important law in computer science that tells us that all problems can be solved by adding another level of indirection, unless we have problem with too many levels of indirections. So let's start with typical monolithic application where we have single executable that is tied into specific hardware platform or QEmu platform that links several static libraries. These libraries provide different capabilities like driver for communication system, driver for power controller, some scheduler, communication stacks, stuff like that. And main application is responsible for building a composition route, wiring different things together, initializing hardware, connecting higher level drivers to low level drivers, and running RTOS, setting up tasks, building everything together so we can achieve our desired functionality. So what we do to switch between QEmu and hardware easily is that we convert main application to static library and remove all target-specific functionality from it, and moving that platform-specific things into runners. We can have several runners. They are just executables. In most of our projects, we have one runner for QEmu platform, so it's using EDI for all communication. And we also have a runner for a hardware platform that uses hardware-specific drivers. In that way, the main application and all libraries are independent from the platform, and the code can be shared and compiled only once. And just by linking to a specific executable, we are tying it to a specific platform. From the code point of view, this is a bit simplified solution, but shows the idea. The main application defines interface that has to be implemented by different runners. So in this case, it's a pure abstract class which provides us with accessor methods to I2C driver and CAN driver. There is also a single global function that provides us with reference to implementation of the peripherals class. For QEmu, we have QEmu peripherals implementation, which is using EDA-based drivers for I2C and CAN. And these references to these drivers are returned by implementation of methods from a previous slide. And this runner provides us with main functions, so the entry point to the application. We can use command line arguments. This is a nice thing provided by semi-hosting. We use these command line arguments to pass values that are passed by bootloader on hardware, but here we can use just command line arguments. In particular, we are customizing our URLs for EDI, so we can have concurrent integration test runs on CA machine without conflicts. Inside main function, QEmu peripherals are initialized, so all hard or QEmu specific things are started here. And after that, we are jumping to entry point provided by main application. Similarly for hardware, we have hardware peripherals class using MCU specific drivers. Also there is main function, this time with no command line arguments because there is no command line for hardware targets. If there are some arguments passed from bootloader, we need some target specific way to access these arguments. But similarly to QEmu, we are initializing the hardware specific stuff and also jumping to main application entry point. So we are using QEmu and EDI and the structure of application I showed you on the few last slides by whole team for over 2 years. Whole Oryx was developed is developed using this software. we have a huge suite of integration tests that can be switched between running on QEmu or on hardware just by changing command line argument in PyTest invocation. And it's really nice because we can share our tests between these platforms and make sure that they work on different platforms. Our Jenkins is running both the suites on every build, and you can see that hardware is a bit slower than QEmu, like twice slower than QEmu. And what is most important for us, that most of the problems we had and bugs we introduced in our code base were found on QEmu. So stuff like stack overflows, deadlocks, some running overwriting some important memory parts. We found that on QEmu without touching hardware. Most of the team is not using hardware on daily basis. We are basing only on QEmu, and the hardware is moving between team members as needed. After a year of development, under QEmu and very limited development board, we had a lot of code. Then we received our first engineering model from our supplier. We added few missing drivers, executed run it on hardware platform, and it worked. It was very, very nice because there were no very important bugs when we used target hardware for the first time. The whole high-level functionality was working correctly. So that was really nice. And during this year of development, we found a lot of issues with compiler, toolchain, and linker playing with us. And if we started solving this problem after a year of development, it would be pretty hard to do it very easy. What we discovered in the last few months is that porting EDI to different architectures, different machines, is very easy. We started with ARM Cortex-M only, then added support for Cortex-R. Then some projects started that were using Atmega's Spark, and porting EDI to these architectures was just a matter of implementing glue to interrupt controller. Also, when we started working on project with Leon 3, we didn't have any hardware with Leon 3, but we needed to start with something. So even run some hello world, handle interrupts, and we started with using only QEmu. And it was really nice because there were already support for Leon 3 in QEmu. And we had some problems with handling interrupts and using interrupts in Spark. But just by investigating the source code inside QEmu, how different things are connected together, by studying the source code, we understood what is happening inside CPU, and we could learn something about this architecture without digging through poorly written manuals and datasheets. But we could just investigate what's happening in the source code. If you'd like to play with QEmu, on our company's GitHub there is a fork of QEmu. It's not up-to-date version. It's 5.1 version, so like year old. We are in process of upgrading into the upstream, but it's still pretty up-to-date version, and it has support for EDI, all these virtual machines I told you before, and few extra things. There's also a repository with headers for EDI, two headers describing the memory mapped IO API, and a bit of documentation. And on my GitHub you'll find a demo using QEmu with EDI with Python to demonstrate how different things are connected, and also following the structure allowing us to separate QEmu and hardware specifics from main application. So thanks for watching and listening. If you'd like to talk with me about space stuff, bare metal development, or QEmu itself, using EDI or developing things for QEmu itself, because it's quite interesting platform. There are a lot of different peripherals already built in. You can reach me via Twitter, or you can send me an email. The contact details are on the slide. So thanks again for watching, and have a good day.
All right, lovely. Thank you so much. This was Maciej Nowak. Thank you for your talk. And don't forget about our virtual escape room. Check our website right after the conference. Hackdive is waiting. Welcome back. This is Code Dive 2021 and our next speaker is Maciej Narojczyk. Now, this is what Maciej has to say about himself. He says, I am no C++ expert, never was, never will be. Who am I? One of the C++ fans. So, rapid prototyping, embedded devices in Python. Maciej, the internet and our attention is yours.
Thank you very much for this introduction. Hello, everyone, and welcome to my second talk at this conference. So we'll be talking about the rapid prototyping embedded devices in Python. So currently, well, maybe in the past, every time we developed something on embedded devices, we used first bash scripting or something similar to quickly verify if the device behaves as we expect before writing the C or C++ code, right? Because going through the cycle of developing C and C++ code on your host machine using some SDK, then compiling for the target machine, deploying that, running that just to see that you actually did access to the wrong register, and then fix the code, again the same thing. So it's way too slow, right? So I believe that everyone first try to prototype everything in the bash, like using the I2C, bus, GPIO, or maybe direct memory access using the defmem command in Linux in case of when the embedded device run on Linux. But since the devices get more advanced nowadays, the vendors do not provide register maps where we could access our device and then configure it with the register reads and writes directly, but instead they provide us with their own libraries. They are often closed, so we do not see the source code, and provide some API in C or C++. So we have no register map. We do not know. We could not access the device by registers anymore. We do not have the source code, so we cannot look into the source and see what's happening there to play with our device. So we have only the API and we have to use it. So are we forced then to use this cycle of compiling on the host machine with the target compiler, then deploying that on the target, running and seeing the results, and again the same thing? Well, no, because we can't use Python, which is an interpreted language, and run the Python on our embedded device directly. But the problem is that not all vendors provide us with the access to the device via Python, any sort of access, right? So they only, most cases, give us only the C or C++ API to do that. But then we can roll our own Python bindings. There are existing libraries for that. For example, with Python or PyBind 11. There are many others. But using those libraries alone or directly is again painful. First of all, you have to manually write all of those Python bindings yourself. there are some generators, but those generators often need some kind of customization, are written in different languages, and C++ types do not match always exactly to Python types in every case. So one case that is matching is not perfect is the C++ pointers to built-in types like the int pointer and void pointer or function pointers, which we see all the time in in our APIs from our vendors, right? They are used heavily. So that is definitely a problem, number one here. So even if you try using the Python bindings generator, it will tell you, hey, you are not allowed to have a binding for the int pointer and so on. Then you are left with either writing wrappers on your C API from the vendor, or that, let's say, do not use those low-level pointers, but instead use, I don't know, string instead of constant char pointer and so on, and then bind that, right? That's a lot of work. And the whole idea for this presentation is that we can really use our vendors C or C++ libraries in Python with zero effort, right? That's what I wrote in the abstract of this talk. Of course, to do that, we need some components. So one of them is code generator that that can be easily customized, and that was let's say the topic of my other presentation about the static reflection. So using static reflection to generate to parse the C++ code and then generate anything you like in ultra easy way for any C or C++ developer. But the second thing is that the Boost Python or any other Python bindings do not support those things directly, so we need to transform all the function and stuff in the API sometimes to be friendly to our binding library. And that's why the missing component in this whole, let's say, path from getting the library from vendor and using it in Python. So the missing component here is this is the support for the missing features in this Python bindings library that exist now. So I wrote that I wrote this library for one project in Nokia. I called it Python wrapper because it automatically wraps existing API from your vendor into API that's easy to use that's friendly to your binding library, and it actually right now it works only with the Boost Python. It's prototype, let's say, maybe not prototype phase, but it's more or less hack around hacked around and then proper engineering, but it fills the gap. In this talk, I'm not going to talk about this library. Just keep in mind that to have this perfect framework to use those C and C++ libraries in Python, you need that in the solutions that I found and I will be presenting here. But I think I'm going to release this to open source, maybe, if I have the time for that. Or you can contact me directly and I will provide you with this implementation details, how I did it, and the source code. But okay, so this Python wrapper library is not the subject of this presentation. But just keep in mind that this is the missing piece here as well, right? Okay, but for now, let's focus on the simple case that we have this, let's say, a library from our vendor that's friendly to our bindings. Library in C or C++, we can bind it without any extra effort. Okay, one thing to note that I think I said that already, maybe. Okay, never mind. So let's begin. So the first thing that we need to do for the C library is to get the Python bindings, right? So here are a sample class, very trivial. It's supposed to represent the API of our library, C or C++ library. So we have here a simple dev class that represents the code developer. We have this interesting things here that I marked red in red font. Well, I did that because I wanted to convince you that this class is not copyable or it doesn't have any support for serialization at all. You cannot serialize that from Python, right? That will be needed later. Okay, so we have our bindings. We have our class, then we write those bindings. We write them by hand. Of course, this example compiles and is runnable. I checked that, so you can try it. So, so this is the manual code you have to write for each function, class, and so on, unless you use the code generator that I talk about in my other presentation. And so here I use this boost non-copyable template trait to mark my dev class as the class that is not copyable. Okay, so when I write this code in C++, I compile this, I end up with a Python module written in C++, and usable as a binary, right? It's not Python code. This Python module is not a Python code. It's just a binary. So we have an example of usage. So we import the bindings. We make an instance of the dev class. We set the name, age, some keys, and we print that, and we get an output, right? So this is basic stuff, right? So at this point, we have Python bindings for whole of our API. And we can use it in Python. That's all great. But if you are using a vendor API library from your vendor to develop something on the target, so to prototype an embedded device, then you simply very quickly notice that you need to preserve the state between invocation of your scripts, right? So in Bash, there is no state in software because each line with devmem, I2C or whatever pretty much spawns a separate process, do something on the device and exit. So basically you can configure a bit your device, then close all application, whatever you have, or exit all Bash scripts, and then open another Bash script and continue from there. But with the libraries, this is not so easy anymore. So you need to preserve the state, which is somewhere hidden in inside the memory of the process, and is created basically when you call the init function from your vendor's API, right? So now you end up with two options. Either you do not leave the Python scripts never, because if you do that, you lose all your settings, and if you want to start another script, then you have to call the initialize again to be able to manipulate this library. But if you call the initialize from the API, the device probably will be reinitialized, all the current setting will be lost. So either you do not leave that at all, do not leave the script at all, or you can, for example, try to add serialization to your vendor's API if it doesn't support that, and probably it doesn't. Serialize this to a file, exit. When you want to continue with another script, then you load the serialized data and continue from there, right? But as I said, the vendors do not provide the serialization, mostly for their APIs, or so then you can try to write the serialization yourself. Well, it's not, most cases not possible either, because aside from the fact that it will be really painful to do this, so it's not possible because the vendor is using some kind of PIMP idiom, so private implementation idiom for C++, or simply void pointer in their structures in case of C, with matches to something that's entirely unavailable because it's only available in the source code, and you do not have the source code from the API. So the standard solution to this problem is to never exit from your Python script, and then start some kind of loop that will accept some kind of messages, or will communicate with your external scripts via messages or some kind of pipes, Linux pipes, to send the text, and then you have to implement this, let's say, daemon or server. So basically, after a while, you look at your script, and you end up with your own implementation of a server when you can accept messages from other servers, and the server never exits. And then you can write your code in your other scripts, right? But that is very problematic, but because for each time you want to call some API function that we have all the bindings for already, because you use a code generator to have them. So you need to write a handler for each function inside your server, for each function you wish to call from a client script, right? Yeah. But anyway, this is the standard approach to deal with this issue, right? You can use some external, some open source libraries that will help you with that. Will either generate some XML format for communication or JSON or whatever. But that is still some effort for you. And yeah. And this is where the point where I found this really great RPC library called RPyC. It really is great. I will soon show you why. But before that, let me come back. I forgot one slide. Yeah, so this is a proof that I tried to serialize my dev object, and I'll at least copy it here. And it fails because it seems that the copying requires your class to be pickable. Pickling is in Python. Pickling is the same as serialization. So the Boost Python bindings say that no way you cannot. You didn't provide serialization for your class, so there's no way you can copy this, serialize, or whatever. So why did I explicitly didn't provide that, and I'm showing you that there is no serialization for that? Because this Python library is written in C++. These Python bindings are written in C++ and are compiled using your target compiler and are deployed on the target embedded device, right? So serializing classes and objects from this your vendor API via those Python bindings to your and sending them to your other remote, let's say, client in Python is really pointless when this remote system is on totally different architecture, right? So if my target machine is for example ARM device and my PC is Intel architecture, CPU architecture, then I cannot execute the same code on the PC and on the target machine. I need to have I would need to compile the API separately using my host compiler to be able to deserialize this on my remote machine, on my PC, to be able to manipulate it and send it back and call the API, right? So this is one thing. One issue with Python bindings, and it turns out that this RPyC library is actually perfectly matching those requirements for RPC calls that we need in the embedded device. It is really the perfect solution. Because one of the main features of this library is that you do not have to have serialization at all for anything that you wish to manipulate remotely. So if I need to manipulate, if I need to want to call a function from the API on the embedded device on my via RPC on my PC with Windows, for example, then I do not send anything, any serialized object between those two machines. And second thing is that I can, in this RPYC, I can call the remote functions even if I don't have anything installed on my remote machine. So no kind of intermediate format of those functions that I want to call, for example, in the form of XML or some kind of proxy libraries in the form of Python or whatever. You don't exactly do not need anything. You just need to have on your remote system installed the RPYC library, Python, and that's all. So this simplifies a lot all the deployment because you only need to provide a environment where you deploy something on the target machine and you do not install anything on your remote PC. And that is really great. Okay. So now, how do you expose your Python bindings for remote clients to use? What do you need to do? Well, do you need to write something manually for every API? Do you need, if yes, then do you need to, can you use some generator for that? Well, the answer is you don't need to do anything. You need to run this one. You need to write this one line of code here, which imports your bindings to inside my service Python class. And this is really old. So this is exactly zero effort as I wrote in the abstract of this talk. You literally do nothing to expose any Python library. Doesn't matter if it's bindings, if it's Python bindings for C or C++ library or standard Python library. It's the same. You just write this one line and you're all done. So I am not a Python developer. Actually, I cannot write Python code at all without going to the Stack Overflow, even for simple loops and if statements. I use it a bit, but when I find out that this is all you have to do, I was really amazed, right? So this is the perfect solution. You do not write anything at all to use your library via RPC mechanism, right? Yeah, but that's not only how this library surprised me. So, but let's focus here on this slide. So we have a few lines of code here. So first, we have this class store when we'll be storing something on it. It's currently empty. I'll later talk about what is needed. Then we import the RIPC on the target machine. This must be available. This library must be available there. Then we implement this single thread server class. So the RPC, this RPC mechanism, the library provides already some different servers, models that behaves differently. So one of them, for example, spawns a new thread for each connection. Other one spawns a new process for each connection, and so on. But what we need in case of embedded devices is often a single-threaded server, so that only one connection is possible. And when this connection closes, each following connection will use the same thread, because there is often a requirement for using vendor libraries for embedded devices that you can access your device only from one process instance at a time, and even more restricted, that you can use only one thread in that process to access the device. So you cannot have multi-threaded access or multi-process access for the device via these APIs that your vendor provides you with. So these 2 lines of code implements a single-threaded server. And then we write our service that runs in the server, in this RPC system. And with that, in this service, I'm doing 2 things. I'm creating the instance of the store class and importing all the libraries that I wish to expose so that the RPC clients can access. And I start this server, so I make an instance of the server, and then I call the start method of it, and then the process that's running the script blocks and loops in the start forever. Okay, and here is the client, RPC client. So I added some colors here, not that it should, because I wanted slide to be prettier, but that to mark the lines of code that are different from the case when I'm manipulating the Python bindings directly without the RPC, versus this example when I'm manipulating the API via Python bindings via RPC. So these green lines at the top is the only difference. On the whole usage is exactly the same. Actually, it's identical that you cannot tell the difference if you didn't have those 3 lines at the top. So this is really amazing again. So another great feature of this RPC library in Python, that there is basically no send message, no receive message, no deserialize, serialize, and all that stuff that's typical in C++ RPC systems, which we use everywhere, right? In here, the RPC generates everything in Python what you need. You don't even have to care. And generates proxies that look exactly the same as your API as your code inside the libraries that you are exposing. So I was really surprised by this library. Again, I never used an RPC library in Python before, but when I found that, I was shocked that it's really even possible in Python to achieve this, right? And I knew that Python is different than C++. Of course, so one main difference for RPC is that it can generate, that you can treat the code in Python as data, right? And you can serialize a function, for example, send it over to another node, another process, and then deserialize it and execute it there as if you have that function on this another node from the start. So, but I really wasn't expecting such a high level RPC library. Yeah. Okay, so here is the running of that. So this number in red is the thread ID that is actually printed on the server side, not on the client side, because this is printed in the C. In the C++ code, we are printing this inside the where am I function. We are printing this thread ID. So I print it here to show you, let's say, the proof that this actually executes in the same thread on the server side, because this is really important. And here is the second client, right? So the second client script, when executed, connects to the server, and it doesn't set anything. It just accesses the device that is the dev object that is stored on the server, and printed name, age, and skills, and so on. And again, the device is the thread ID is the same. So this John 21 C++ Python, those strings print on the client side, and this red line prints on the server side. But I just copied it here like that. So what we need to do so that the second client can access this dev object and continue processing, right? So we need to set it on the server side, because so we use the set attribute call in Python to do that. If we do not do this, the dev object will be removed once we exit the script, right? By the garbage collector. Because even if we know that this device dev object is actually the reference, but this is a reference to an object that resides in the server side heap memory, right? So here it looks like I'm creating a local dev object on this client side, but you have to remember that dev object, dev class is not serializable and not copyable. So there is no way for the client to be able to create an instance of that, right? Unless it imports the bindings directly here. But if we assume that this client runs on the remote machine with the Windows where there is no such module at all, because there cannot be, because binding module is a Python class, Python module, but it is in the form of binary code compiled from C++ code, and we do not compile our API for Windows. So we do not create this dev object inside the process memory space of this process, of client process. Instead, what we have here is the object created inside the server side process, and here we have a reference to it. Of course, references across processes is not possible in Python, I think. So this RPC library implements this something called as net references. So we have the dev object, which is in fact a net reference to an object that resides in the memory space of the server, right? But we manipulated on the client side. So even if it's on the server and the client closes, well, when the last reference drops, the object will be destroyed. So that's why we have to explicitly tell server to keep this object in our in the memory inside the store variable, right? So the store variable will fill up with our objects as we run more scripts on the remote side. Okay. Here I have one picture that's supposed to more clearly show you the deployment and what's happening here when you use this RPYC library. I hope it it explains more and makes this a little less confusing, because honestly, when I'm using this, I get confused what is called on the server side and what is called on the client side, because obviously you can mix your calls to the function that you have defined on your remote side with the one that are on the server side, and the syntax looks exactly as if everything was available locally. So after a while, you will, at least I am, lost what's where, right? This is such a high level of abstraction here, provided by this library. Yeah. So in this picture, you see that on the remote machine, all you need is to import the RPYC library and nothing more. You don't need to have this bindings module, proxy, generated XMLs with method definition, really nothing, right? And this remote client doesn't have to be on the target machine even at all. It can be anywhere where you can run Python. And this let us, with zero effort, achieve our second need for rapid prototyping. So first was that we do not go through the C++ compile with SDK, deploy, run on the target, and check what the output, and again get back to the host machine, compile, deploy, and run, and so on. So we just compile our bindings once, we deploy them, and we run our scripts, right? But running scripts and writing scripts on the target machine is pretty inconvenient, right? After all, I want to reuse my favorite IDE for Python, run it, and inside that write the code as if the embedded device was really a part of my host machine. And with this library, you can do that. You can write the code in your IDE, even if in the same way as if this API from your vendor was in Python and it is runnable on the host machine. And this is what I call really rapid prototyping here. So first Python, secondly Python on the remote machine, and the most important thing is that you need to generate Python bindings once for the whole library. You do not add any single line of code on your server. Expect this one import, and you can prototype until the end without going back to C++ again, right? So I think that this is like the perfect solution here. And with this RPC library, it is possible. So with such great tools, you can separate the work in your team, split the work between a developer, C++ developer, who will prepare the bindings, turn your, let's say, C++ API to Python, set up an RPC, and he can do this once without even knowing what this API is all about. He doesn't care. He can even set up a script that would generate that and and deploy on the target machine, which will accept just, let's say, a name of the library from which to do this. So he doesn't have to have any knowledge about that. And then another person in your team, so a hardware engineer, for example, who knows Python and doesn't really care about C++ and doesn't want to deal with all the pain of using C++ in embedded devices with the SDK and so on, or Yocto, if he has Yocto. He knows only Python, and he can then, once he gets the package which he installed, he doesn't need anything more from the C++ developer. He can then prototype everything by himself. Yeah, of course, if a new version of the library from vendor comes up, the C++ developer has to update, but because it's all automatic, he doesn't really have to do anything. It's quick, right? So the important thing is that unlike other RPC mechanisms, when you have to write a ton of XML stuff for each function, and probably you are adding those those bindings for those function, not binding for this support for your methods from the API in this XML for serialization one by one, depending on what is needed. You do not do this all the time. So two developers are involved constantly and have to wait one on another. So the Python guy has to tell, hey, now I need this method. Please add the serialization and a handler in your server for this, because otherwise I cannot continue. Or even if this your current, let's say, RPC system generates everything beforehand, then I really didn't find any other RPC system that provides syntax on the client side that is identical to the syntax on the target machine. So when you basically run your script directly on the target, you can easily go with it to the remote machine and execute it there with just changing this 3 lines of code. Okay. So let me talk about let me first summarize what I said and what you need for such a rapid development with Python of embedded devices, right? So first you have to get so you have a library from your vendor with the interface API in header files. You don't need the implementation. Then you need to generate bindings. And first thing, right, generating bindings. And that can do this manually, but that is really painful and very troublesome to update each time the vendor updates. So for that purpose, I suggest using some kind of generator, right? So I rolled out my own generator using static reflection, and if you go and check my other talk about that, you'll see how easy it is to do it. And so code generator is the first thing. Second thing is that every Python binding mechanism I know doesn't really support all the basic and low-level stuff from C++, from C that is used in most of those APIs. So, for example, pointers to built-in types like the int pointer or void pointer, which do not map, do not have a mapping in Python, direct mapping in Python, and standard, let's say, function callbacks from C, right? I do not talk here about the std function, but plain old C function callbacks. So you need something that will allow you to automatically wrap this, bind this, right? So I wrote this Python wrapper library, which I can share with you if you're offline if you're interested. So once you have that, we have a wrapper generator that generates Python bindings that support everything that is common in C. And then we, with single line, expose that all to the RPC system, right? With the RPYC library, which is so great that it allows you to access this server from any remote machine that has Python and nothing else. Really, you can even do this from a McDonald's screen in McDonald's restaurant that if you hack it around and get access to shell, you can connect and install Python then and do it from there. So this is really great. Okay, so the alternatives to worth checking here is mentioned in this list is PyBind 11. So this is basically a real implementation of Boost Python using C++ 11 syntax, so it's more lightweighted and compiles much better. But it has probably some new features maybe, but it doesn't still handle all this low-level stuff in C, so you still need some kind of wrappers for that. And this from the fourth point, the CPPYY can be, or maybe it is, I didn't try it, but from what I read, it's really maybe a game changer here, because as it seems, using this library, you actually do not have to do anything at all. It generates the bindings on fly, and even more. I suspect that it can even on fly generate bindings for template instantiations. So for example, if you have a list template in C++ and you want to bind it to Python, so you can only bind, for example, specific lists. For example, list of ints, list of your own class, and so on. You have to do it before you start playing in Python. But with CPPYY, it's actually probably possible to generate template bindings on fly, because this library is using just-in-time JIT C++ compilers. So specific implementation for this is the Clink compiler. So based on the Clang, that can compile C++ code on fly, right? Just like it would be an interpreted language, right? Just like Python. So downside, I didn't try it because, well, lack of time. Obviously, I need to ship something before the deadline. But the downside I see is that it is heavyweight a bit, because you need to deploy on your embedded device at least the whole Clink interpreter, which is probably 50 megabytes or more, and then this library. But I really recommend to first check it out, or or at least try it if it's suitable in your case before going to other Python bindings solution. Yeah. So this is all from me. Thank you very much for listening, and I hope you enjoyed.
Great talk. Thank you very much. This was Maciej Narojczyk. Thanks a lot. This is Code Dive 2021. welcome back, and let me introduce the last speaker of the day here on Stream A, and the speaker is Konrad Kolski. Konrad is an application engineer at SciTech Software, oprogramowanie naukowo-techniczne in Polish. The company is a MathWorks authorized reseller for Poland. Working with MATLAB and Simulink, he is responsible for presenting or promoting its technical capabilities, consulting customers' product development workflows, and helping with the transition to simulation-based approaches. He's also engaged in training engineers from commercial companies and educational institutions in the advanced use of Simulink software. He specializes in model-based design methodology with a focus on embedded software, VNV, automated code generation, and control system design. He has a master's in mechatronics, and today he will be talking about automating code generation for embedded systems. Konrad, off you go.
Hello, my name is Konrad Kolski and I'm application engineer at ONT. Today I want to talk about automating code generation for embedded systems. Automated code generation is nothing new. Tools that achieve this task are present for many years now. Some of them would create only partial code, like code architecture, where we place our algorithms in predefined places, while others could actually write source code for the programs we want to create. The latter ones especially could be source of some controversies, just like with any other task when we are handing over part of our job to machine or computer program. We can have doubts if the task is going to be achieved according to our intent and if it's going to work just like we want. That's why today I want to not only talk about automated code generation, but also give you an example how it's done, and most important, show that automated code generations is not something to replace handwritten code, but it's just another tool to make programmers' life easier and make their job more efficient. And such tool that is supposed to support us in writing our algorithms in order to be suitable for high integrity workflows that often are subject to safety and security standards, it needs to meet few underlying requirements. First one, quality. Of course, we want to generate high quality code, bug-free, ready for integration and implementation. The tool itself should be very consistent. This means that through all the generated code, variable usage, function naming scheme should be built in the same way. With that, every person using such tool, working in the project, in the team, will be able to easily understand and go through any generated source file. Productivity is also an important factor when we talk about automation, of course in terms of code generation also. With constantly updated and developed algorithm, we should be able to run the code generation iteratively, and it should produce each time a new iteration of code that will be updated with every change we create, and such updated code should integrate seamlessly with the overall project we are working on. Last but not least, if we are generating the code, we need to have some sort of source of this code, some way to describe our algorithm and tell the tool that this is the program we want to write. And with that in mind, we should have some level of abstraction when we can create, for example, a model of our target code, and this model will dictate functionality we want to implement, and with that when we are developing our algorithm, we are developing our model, which becomes the source of the code that generator is creating. And of course, meeting these 4 requirements will give us the benefits of automated code generation. First of all, if we are using same tool for writing our code that is constantly developed, updated, and kept running, the quality of the tool that increases over time increases the quality of the whole code base we are using. Every project we made in the past can be updated in the future using the newest version of the code generation tools. If it's a tool that is working according to specific templates and schemes, the code is of course consistent, and with that it's easy to understand, use, and layer more functionality over it. In terms of productivity, the tool is working on specific source, in this example a model, and with that the constantly updated model gives us constantly updated code that can be changed over time based on changing requirements. We don't have to go into the source itself and modify everything line by line, but we generate these changes, these updates on the higher level of abstraction, and the tool automatically converts it to newest version of our source code. And last but not least, if we are using this model as something that is describing our solution, our algorithm, and the coder is like a plugin that will read the model and then convert it to specific source code, if we can change the code generation, for example, to other plugin, we can easily retarget our solution to completely different platform, not just other microcontroller, but for example PLC or maybe FPGA. Without doing anything manually, we still work on the exactly same source code, and all the work is done by the new code generator. And one of such tools is Embedded Coder. It allows us to generate standardized ANSI ISO CC++ code. It's important to note here that it's production code. This means it's optimized for specific processor architecture. Additionally, even if the code is generated automatically, user is provided with necessary interfaces to customize the source code. For example, we can control all the data types, we can specify function interfaces, control variables and their storage class or code memory sections. Additionally, the code generation process can be also optimized for specific goal like execution efficiency, traceability, debugging, or we can focus on safety considerations. And as I mentioned earlier, we have means to customize our code not only on the algorithm level itself, but also on the whole project level, if I will say so. The tool is using specific code generation templates, and we can also modify those to make sure that our files are organized in specific way, or the inside structure of the files is made just like we want. For example, exactly to the specifications of overall project or solution we are working in. Last but not least, Embedded Coder provides verification mechanism where we can run our code as standalone application, because it also generates the main program either in single rate or multi-rate multitask execution mode, and we can run the standard software in the loop or processor in the loop verification process to test if our source code and the compiled code is actually giving us the same results as source model we used to describe our algorithm. And last but not least, the generated code is not a black box. This is one of the main concerns where people hear about something that writes code on its own. The generated code is fully available to user. It comes with a report where we can go through it line by line. The code itself contains many comments that gives us better understanding of the code. And of course, the source files are fully editable, customizable. We can take, for example, only part of the program and place it in our project, or integrate all the generated files in bigger solution. And so, if we are not going to handwrite our code, how else are we going to describe code generation? What exactly we want to create? Answer to that will be Simulink. Simulink is block-oriented environment for system design. It enables you to design your system with multi-domain models, simulate them before moving to hardware, and deploy them without writing code. It integrates with model-based system engineering workflows, so we can not only work on singular components, but also design, analyze, and test whole systems and whole software architectures of our solution. It integrates with requirement management tools and supports automated workflows such as continuous integration. Alongside, we have Stateflow environment that is focusing specifically on state machines and event-based logic. And of course, all of these, Stateflow, Simulink, and Embedded Coder, are working on top of MATLAB, which is most known as programming and numeric computing platform to analyze data, develop algorithms, and of course create models. MATLAB itself is home to many toolboxes which provides algorithms for different industries and different applications. Simulink, Stateflow, and Embedded Core are such toolboxes. We can use pre-made, ready-to-use, out-of-the-box algorithm, for example, for signal processing, designing wireless communication, control systems, or image processing and computer vision applications. With that in mind, this gives us another benefit of automatic code generation with Embedded Coder. If we have all these toolboxes for different applications ready to be used and all supporting code generation, algorithm developer now can focus on how I'm going to solve the problem that I'm facing, instead of spending their time on handwriting every single line of code that needs to be written in order to make the program run. Last but not least, all these toolboxes, MATLAB, Simulink, and this code generator, Embedded Coder, is not here to replace everything we've done before. To prove that, MATLAB and Simulink can easily integrate with other programming languages. For example, C, C++ libraries can be implemented in our model as own custom blocks. They will be used for simulation to test our solution, and later for code generation to provide final implementation. With that, we don't have to rewrite everything we've done before. Instead, we can use it in future projects, future solutions, if our designs are already well tested and well documented. And so, now that we know how are we going to generate code, let's discuss the code generation workflow. It consists of 4 main steps. First of all, target hardware selection, then model configuration, code generation optimization, and source code review and traceability. First one is all about telling embedded coder what actually we want to program in future. With that, we can make sure that our source code will be as ready for implementation as it can be. This generic code generation configuration applies some code generation presets for most popular embedded hardware vendors. It's mostly related to supported data types and bit lengths. In some scenarios, it allows easier integration with third-party IDEs. Of course, the list is limited, but we have this option to create our own custom processor definition. If that's not enough, then we have the capability of developing our own custom hardware target. In this scenario, we are fully customizing all the code generation templates. We create own code generation setting presets and custom parameters. We can provide external libraries and drivers to make sure that generated code will use all the hardware capabilities of our device. Last but not least, we are instructing Simulink embedded coder what kind of tools, compilers, linkers, and programmers it's supposed to use to generate the code, compile it, and implement it on our device. So in this approach, we have complete solution from designing the algorithm all the way to the final implementation in embedded processor, everything according to our customization. And if that's too much of work, because let's face it, it requires a lot of practice, Embedded Coder, MATLAB and Simulink comes with so-called hardware support packages. They allow such direct implementation on most popular hardware vendors, including ARM devices, Intel NXP, ST Microelectronics and Texas Instrument devices. These hardware support packages apply hardware-specific configuration to code generation settings. For example, they configure hardware interrupts, timers, configure communication interfaces, and so on. They also come with I/O drivers, such as MATLAB blocks and functions, so we can model not only the algorithm itself, but its connectivity too. For example, acquiring data from ADC converters, processing it, and then sending signals to other data channels such as I2C or maybe CAN. With that, we can create again a full solution from modeling and generating code all the way to the final implementation. Next step in code generation workflow is model configuration. In here we specify, for example, all the data types, all the sample times in our algorithm. Then we move to optimization to tell embedded coder to either focus on, for example, pure code execution efficiency, or maybe focus more on safety considerations. Last but not least, when code is ready, we will performing some kind of code review and maybe perform traceability analysis to see which part of code are implementing what parts of our model. And how it looks in practice, this is the time for our example. What I have here is Simulink model of Gerrit algorithm. It consists of Simulink blocks and state machines from Stateflow. It takes two input signals, speed and throttle, and converts them to gear output for other devices in our system. In here we can see that these signals are being used for calculating thresholds to switch gear up and down, and state machine controls when should we change to which operating mode and send a signal to either increase the gear or decrease the current gear. Now let's simulate our model by placing it in test harness. In here I have some example signals, test vectors. With them I can check how my program behaves and reacts to them. Additionally, the model itself is placed in here by use of so-called model reference. Practically, it makes sure that any input signal properties won't affect the properties of model itself. For example, they won't change its sample rates or data types. Additionally, whole harness is configured as baseline test because I have this third reference signal to see if outputs from my program are exactly as I expect to be. Let's press Run button now to simulate model and then check all the signals, how they change in time with use of Simulation Data Inspector. And in here we can compare everything and see that with increased speed and throttle, gear also increases. Everything works as expected. Let's now configure a model for code generation. First of all, we need to select system target file. This is how we basically tell Simulink what kind of code it should generate and with which coder. We are going to pick ERT-TLC system target file because it's using embedded coder to generate production C code for embedded systems. Of course, there is also option to generate C++ code. If we open the list of all available system target files, we'll see many of them provided by different toolboxes. We could, for example, generate more generic C code, more suitable for desktop applications, or for example, generate AUTOSAR standard code for automotive systems. After that, everything is ready for code generation. We also can select the generate code only option to make sure that no compilation will happen, because right now we are focusing only on the source files. Earlier I mentioned that user can customize properties of the model such as data types of signals, variables, and for example sample times to make sure that they appear in generated code exactly as we want them to be. So we can do it, for example, on the import side of our model, and those properties will be inherited through whole algorithm, sample time or data type, and on the list we can see that Simulink supports not only integer data types of different bit lengths, but also floating point data types such as double, single, half precision numbers, and fixed point data types. And when we generate code with those types, of course, all appropriate conversions are being implemented in the code itself. We're going to see it in just a moment when we actually generate our code. For that, let's open Embedded Coder app first. This way we are going to access all the code generation functions. There it is. And now let's prepare the code generation report because we are going to see some extra information in there. First of all, let's enable the report generation and traceability between code and model, and other way around. This way we are going to trace exactly from where our code comes from. This applies both to Simulink blocks and stateflow charts. Additionally, we are going to enable additional static code metrics that provide information about source files. And now that everything is done, let's generate the code. One click and everything begins. In the diagnostics panel, we can see how it's happening, how Simulink is literally writing source files based on the system target file we selected. We can see code generation happening in here. And additionally, if we also ordered tool to build our application, we will see that toolchain is being invoked. And finally, we can see that HTML report is created. We are going to inspect it later. So, where are the source files? They're always placed on the hard drive in localization specified by the user. By default, it's current working folder, and there we have the folder named ERT-RTW with model name at the beginning. In here we are going to find all our source files that were created just a moment ago. We can open them, edit them, do everything we want with them. Additionally, the code itself can be inspected through the report, the HTML report that was created automatically. And additionally, we have a code panel alongside the original model, so we can easily track everything and see where it comes from. And with that in mind, let's see how it works. Let me click any component on my model, and instantly we can see that the tool is highlighting everything that belongs from this component in the code. This way we can precisely see in which part of the code our schematics are being implemented. We can go really deep to the specific part of our algorithm, to specific, for example, transition condition or logical check. Additionally, it also works other way around. Let me click any of these comments in my code, and as you can see, it instantly highlights any component that is being implemented in this section of source code. Additionally, the code panel helps us navigate through the source files itself. We can select variables, see where is the definition, declaration, and so on. The report is more formalized document. It's in HTML format, so we can, for example, print it or include in other documentation, but it shares same functionality. We can navigate directly from the model to the code itself, and other way around from the code report back to the original model. Additionally, we can see some summary about generated code, date, time, author, and so on, and additional information, for example, the code interface report with all the functions and their interfaces, data types, and so on, with additional information if you are working on scalars or maybe vectors. The static code metrics, it's mostly about the files, their size, how many lines of code, how many lines in total, and variable usage, and of course function information, for example, how many times functions are being called, how many times variables are being written, written, and additional information about memory usage. The code itself consists of several files which will be generated every time we use embedded coder. They will always be there. First of them is the example main file with example file main function, ERT main. In here we have two functions. First one is the RT1 step function. Basically, its function is to call the TCU step function, which includes whole algorithm we just developed in model. The second function in here is, of course, the example main function. It initializes code, terminates code, and in the commented section we have information that in here user, in order to launch this code, should call the ERT1 step function with same frequency as the model is being run on. So in here we have 15 milliseconds. This way we will have our code work exactly as the model during simulation. The initialize function in here is to mostly set all the initial condition in our program. For example, set the initial state of our discrete unit delay block. Of course, developer can include his own custom code in this initialize or terminate section, and it will appear in source files. Let's go back to the code now and look through the first source file. And in here we have terminate function. As in most embedded application, it's empty. We can of course remove this function so it's not taking any space. And as I mentioned, this use step is the most important function in generated code because it holds the whole algorithm. Whole model code is placed in here. And just like before, we can see there are many comments that describe which parts of the model are actually being implemented in here. The code itself is using specific naming scheme and is realizing all the function that blocks do in the simulation. Some additional files include TCU data where parameters have their numeric values. They are stored in structure. It's typical P structure for parameters. This way, with this public global interface, we can tune these parameters, for example, in any external application that we integrate our code into. Additionally, all the model inputs and outputs are also placed in such structures. The EXTU and EXTY structure for inputs and outputs. Of course, we can change that, and we are going to discuss it later. This scheme makes sure that no matter what kind of code we see, as long as it's generated by embedded coder and MATLAB eSimulink, we can easily recognize all the specific elements and navigate through the code with ease. And of course, we have the structure for all the states, so the memory of our code. Beside our unit delay block, in here we have states from the shift control and gear control state machine. There are some extra utility files in here like RTW types. This is basically translation from data types used by MATLAB and Simulink environment to data types used in the embedded environment. So in here we can see typedes translating from, for example, double to real T types. Additionally, there are some macros defined in here for minimal and maximal numeric values that can be represented by each data type used in our code. This is very handy for some functions that are also being implemented by the code itself. For example, in arithmetic division, where there is risk of performing division by 0, Simulink can automatically implement a safety precaution that instead of generating 0 or, for example, infinity in this division, will instead, for example, use maximum or minimal value that can be represented by each data type. Of course, this safety precaution can be disabled to get as efficient code as possible. And speaking of efficiency, to achieve it, Simulink for most of time will inline as much of the algorithm as possible, so everything can be optimized internally during code generation. But if you are interested in any specific subsystem and we want to get a separate function from it, we need to mark it as atomic unit. Then we will enable additional function packaging settings. The auto setting is that if our now atomic component is used only once in whole algorithm, it will still be inline to achieve maximum efficiency. Only when, for example, we'll have multiple instances of this block in our schematic, Simulink will automatically detect multiple copies of this component and then create a reusable function interface that we will be able to see in the code interface report and source files itself. So let's do it now. We're going to force that behavior to happen by duplicating shift threshold component. Let me copy it below. Now let's connect all the signals to the input ports of subsystem. If Simulink sees that component is not actually being used in simulation, or if it does not produce any results, then it will ignore it during code generation. That's why we also need to provide some output interfaces to our block. And there we go. Now let's regenerate the code and see what changed. By the way, when generating code, Simulink checks the checksum of whole model, and if it finds that there are no changes at all to the model itself, then it will just skip code generation and revert to the original code. And there we have our custom TCU shift threshold function generated automatically for both instances of shift threshold subsystem. This way we avoid duplicated inlining of code. And in here we can see a common code for all components. The same behavior, of course, can be forced to happen if we set the correct setting to tell embedded coder that we want explicitly function from this component. So let's go back to its properties. Let me just fix this model and now specify that from the shift threshold component we want to generate a reusable function, because as you can see, you can also force inlining of this component or force non-reusable function interface. The difference between reusable and non-reusable function is that non-reusable function has its own private memory interface, and multiple instances of this block will have the same memory section, while reusable function will separate the memory for each instance of the block. By setting name configuration to auto, we will see that this function is going to be implemented directly in the main source file, so TCU-C. And there we go, we have shift threshold function again, despite having only one instance of shift threshold subsystem. This way, by the way, we can configure code generation so we can separate specific functions of our algorithm into external projects. For example, if something is in one separate function, we can easily move it or separate from the whole project. And if that's not enough, we can customize our function by, for example, specifying its own name, its own source file, and decide how the interface is going to look, if it should use the block visual representation, so the arrangement of inputs and outputs, or should the interface be optimized by embedded coder itself. And let's generate code again. By the way, you can see that in this code panel, all the changes between each code iteration are being highlighted. And there we have my lookup function, just as we specified in block properties. And that's how this customization works. We can easily move any component from the main source files to external file, which can then be easily separated from whole project and reused in many other solutions. And additionally, if we decide this way, we can, for example, generate code only for a specific subsystem instead of whole model. So, for example, if we have a model of whole system, we can just generate code from, for example, its controller instead of whole plant. And last option for non-reusable function. In here we can specify the interface for the function from the default void to any other. And as far as function customization go, we can not only customize subsystem function, but also modify the interface of main step function in similar way as we did just now. And while function configuration is a way to optimize specific parts of the code, you can also make use of global optimization settings to instruct embedded coder on how to shape the code to meet programmers' needs. For that, we'll be using again code generation configuration parameters. Why? Some of these settings are already in the appropriate section, some of them are hidden in advanced parameters sections. One of these is terminate function required checkbox, which can simply delete the terminate function from our source file. Just like we noticed before, it's nearly always empty. And very useful function in here is that if we know exactly what we are looking for, we can use the configuration search bar to get anything we need. Now if we regenerate the code, we can instantly see the difference in source files, either in the source code itself or in one of the code generation reports. And there we go. If we scroll down, we will see that there is no termination function anymore. Other settings, for example, can be related to variable initialization. In here we can altogether remove the IO0 initialization for global input and output variables and the local internal data initialization. If we are, for example, sure that our embedded processor is performing its own hardware memory initialization, or instead of using simple software initialization, we can use specialized memset function. And below we can also see these special functions that are meant to protect our code in scenarios where by any chance integer overflow will happen during, for example, floating to integer conversion. It will then perform either, for example, saturation, or maybe it will wrap out of range value. And same when, for example, a division by 0 will happen. Normally it's impossible to compute it in embedded processor, but doing the calculus and limit calculation, we know that dividing any number by 0, we can actually replace the result with infinity. And in here it will be maximum value that can be represented by any data type used in this calculation. And while these settings are important, they still focus on specific parts of the algorithm. And we want to discuss more global optimization. And in here, in the signal storage reuse section, we can do that. checkbox in here control how embedded coder will treat variables in the code coming from signals in our block diagram. And then if these signals, these variables will be more of the time represented as global variables or maybe local variables. So this is a thing that can affect performance of program significantly. First checkbox globally enables signal storage reuse. So now embedded coder can reuse a variable instead of creating separate one for each expression it's calculating. Next one, enable local block outputs and reuse local block outputs. First, enables usage of local variables within functions. This way the signals in between each components of our model will be represented by local variable in the code. Additionally, reuse of local block outputs make sure that again, instead of duplicating variables on, for example, different logical pathways of our algorithm, embedded coder will use only first local variable to store the results of calculation instead of creating unnecessary buffers. Next we see something called eliminate superfluous local variables expression folding. This allows to completely bypass variables by combining several expressions into single line of code. Last but not least, reuse global block outputs. Make sure that instead of storing calculation results in separate variables, local variables or global variables, they will be written directly to the function output interface. And now let's generate code and inspect it. In the code panel, let's switch to TCU C source files, and in step function we can already see results highlighted. Two local variables RTB vdown vup are here thanks to the enable local block output settings. Additionally, reuse local block output made sure that the same local variable is being used along the whole logical section of the code to store all the results. And finally, also the same variable is being used to pass the final results to the function output interface. This way we don't have to create as many variables as normally would appear in the more debuggable, more traceable source code from the embedded coder, because these settings were used here to focus purely on code efficiency. And while this configuration allowed us to globally decide whether we wanted to use global variables or rely more on local variables, or minimize the amount of variables altogether, the storage class settings will let us decide about every single variable that appears in our generated code. These variables can come, of course, from parameters used by our model, or, for example, from the signals, because as we could see, signals are also variables to hold results of calculation between each of our model component. And in here, in the Model Explorer, we can inspect every parameter, every variable used by the model itself. They can have their own properties such as sample time, data type, dimension, complexity, but also there is this storage class parameter, and with it we can decide that speed signal coming from the input interface of our function should have specific form in generated code. Let's select it and now switch to the code generation section and see what kind of storage class is here available. And here is the list. Does anything look familiar? Because storage classes are nothing more than a way of mapping typical code constructs used in C++ to objects in our model. So we'll have storage class, for example, to indicate that variable should be global, that variable should be a pointer, or for example, it should be a structure, or maybe a local variable, or for example, a bit field. Also, we have a getSet storage class to let user create own custom read and write functions for specific variables if, for example, they required more work to be safely accessed. This way we can shape the code just like we want. And in storage class section for parameters, we see again some familiarities: the define storage class, the const, the volatile storage class to use preprocessor macros. And now let's go to the throttle signal. We select struct storage class for it and specify structure name myThrottle for this specific signal. The speed will now use imported extern pointer, and gear also should be a custom structure named myGearOut. And for VApp parameter, we'll use exported global storage class. Now let's regenerate the code. Before that, let's make sure that our signals are actually using custom definition by resolving the signal to its corresponding object in configuration parameter in Model Explorer. Same for all inputs and all outputs. And now let's see the results in the TCU-C file, the source file. At the very beginning, we can see myGearOut and myThrottle variables. From the command, we can read definition for custom storage class struct. And if we now move to the appropriate header file, so TCU-H header file, we can see type definition for custom storage class struct, just like we defined it. And here are two variables used in the code itself. So with this simple setting, we significantly changed the shape of the code and variable usage. Let's move now to the source file again to look for the other changes. If we remember correctly, one of them was also set to exported global type, and other was specified as imported extern pointer, and there it is, the speed variable. It is being used as a pointer in here, but imported prefix means that its definition is nowhere to be found because user, the programmer, has to provide specific header file with variable definition. And while things that I presented today in terms of code optimization are just top of the iceberg, due to time running short, I will now discuss some extra features of Embedded Coder, and one of them is code execution profiling. In this mode, we are going to run our code and measure task execution time. So how long does it take for single iteration of our main algorithm to complete its execution? We store all the information inside the environment, so later we can analyze it and display all the data on graphs. Once it's configured, let's now perform simulation, which is basically compilation of our code and its execution in separate process running on our development computer. This is basically a software-in-the-loop simulation. And once it's done, we'll have this interactive report which will allow us to inspect results. Let's click on our component, and in here we have table displaying average execution time of our function, maximum self time or average sum time, other information like how many times function was called during execution, and data is gathered not only on built-in function but also those customized by programmers. So for example, our shift threshold custom function, there we have its information, execution times and number of calls. And let's go back to the main model again, and there we'll see that informations, these times, can be also presented on graphs and plots. In Simulation Data Inspector, we can compare how did the execution time of function change over time. On x-axis we have observable time, so real-time clock, and on the y-axis we have execution time of our functions. This way we can, for example, determine that at specific part of our algorithm suddenly everything slows down. And now let's look for the cause of it. If it was algorithm being run on hardware itself, potentially we could look for some hardware interrupt being executed in here, stopping execution of main lab. And as this was software in the loop simulation, so still on development computer, we have of course many other factors in here that could interrupt our routine, including for example Windows updates, but we can't help it. Nevertheless, code profiling is very powerful tool not only to decide if our algorithm is running fast enough or can it be further improved or expanded with more features, or for example we can use code profiling to tell which type of implementation, for example through MATLAB function or Simulink diagram, is more execution time efficient. And as I mentioned, code profiling can be run in both software in the loop or processor in the loop code execution mode. They are all supported by embedded coder, not just for that, but also for general task of performing code equivalence testing. And last but not least, code replacement API is something worth mentioning in here. Basically with that, programmer can replace any function in generated code coming from default Simulink blocks and MATLAB functions with his own implementations, or for example with functions from libraries from hardware manufacturers. And so, embedded coder, beside allowing this functionality, also has own built-in code replacement library for standards such as AutoSAR 4.0, or it has functions optimized for specific hardware, ARM Neuron Intrinsics for SIMD operations, ARM Cortex-A or M processors, and Intel DSP processors. To summarize, MATLAB and Simulink can be used to develop any algorithm in form of readable and functional schematic diagram. It can be simulated, tested to make sure it's working as intended. And then with embedded coder, we can convert it to highly optimized, readable and production C++ code ready for optimization and implementation in target hardware. The optimization mechanism can customize code to meet programmers' needs, and of course, thanks to presence of this intermediate representation language, we can replace embedded coder with any other kind of Simulink compatible coder to quickly retarget our solution from one type of processor to another without need to rewrite everything from the beginning. And that would be all. Thank you for your attention.
Konrad Kolski, thank you for this session. And this is it for this year's Code Dive. This year we've had 14 talks, 2 streams, a very brave group of Nokians preparing the conference, 1 virtual escape room, 1 video crew making it happen for us online, and of course you, the one and only Code Dive audience. Thanks very much for joining. Don't forget about Hack Dive, our virtual escape room. The game is about to start on our website. My name is Rafał Motriuk. I'm a science and technology journalist. It was, as ever, a great pleasure being your host. Thank you for having me. Goodbye and see you again.